We build rockets, sending probes to the farthest corners of our solar system. We gaze deep into space with telescopes that can reveal the faint, ancient light of galaxies billions of light years away. Our technology is powerful, a testament to the relentless reach of the human mind. Our curiosity is boundless, an insatiable hunger to understand the grand, the cosmic stage upon which our fleeting lives unfold. And yet, for all our progress, for all our ambition, there are places we can never reach. There are realms so distant, so fundamentally inaccessible, that they will forever remain a mystery, shrouded in the darkness of the ultimate unknown. These are the forbidden zones of the universe, regions of reality that are lost to us, not because of a failure of our technology, but because of the very nature of the cosmos itself. Some of these forbidden realms are being actively created right now, as we speak, torn from our view by the relentless and accelerating expansion of the cosmos. Entire galaxies, once our cosmic neighbors, are receding from us at speeds faster than the speed of light, slipping silently and irrevocably beyond the horizon of what is possible for us to ever see or to touch. Others of these forbidden zones are buried deep within the most extreme and violent objects in the universe, in the hearts of black holes. Their event horizons are not just boundaries, they are one-way membranes in the fabric of space-time, a point of no return that seals away whatever falls inside, its secrets, its information, its very existence, forever erased from our view. And some of these forbidden realms exist not in space, but in time. The very first moments of the universe's creation, the fiery crucible of the Big Bang, are hidden from us behind a veil of such extreme heat and density that no telescope, no theory, no future breakthrough will ever be able to pierce it. And yet, we wonder, we imagine. We reach with our minds where our bodies and our machines can never go. Could those distant, unreachable galaxies, forever cut off from us by the expanding void, harbor their own unique forms of life, their own civilizations, forever living in their own isolated cosmic island? Forever unaware of our existence, do the dark, silent hearts of black holes conceal the deep, fundamental secrets of the nature of reality itself? The answers to the puzzle of quantum gravity is the true story of the birth of time, of the very beginning of our universe, locked away behind an impenetrable and eternal cosmic curtain. The forbidden zones of the universe are a profound and humbling reminder of our own inherent limits, but they are also a powerful and beautiful testament to our greatest strength, our curiosity. Even in the face of the unreachable, of the unknowable, of the eternal mystery, we continue to ask, to explore, to dream. And perhaps, in doing so, in the very act of reaching for what lies beyond our grasp, we find something just as profound and just as meaningful as the answers we seek. The universe is vast, far vaster than our human eyes, or even our most powerful and sophisticated telescopes, can ever hope to see. When we gaze up at the clear, dark expanse of the night sky, we are not just looking out into space, we are looking back in time. The light from the nearest stars has traveled for years to reach us. The light from the Andromeda Galaxy, our closest major galactic neighbor, has been on its journey for over 2.5 million years. And the faint, distant smudges of light from the most remote galaxies have been traveling towards us for billions of years, carrying with them a ghostly image of the universe in its infancy. But there is a limit, a fundamental and absolute boundary to our vision. There is a cosmic horizon, a spherical shell around us, beyond which we can never see, never explore, and never reach. This is the cosmic censorship zone, the vast and perhaps infinite region of the cosmos that exists beyond the confines of our observable universe, a realm where reality itself becomes, for us, forever unknowable. Our observable universe, the part of the cosmos from which light has had time to reach us since the Big Bang, stretches out for about 46 billion light-years in all directions. This number might seem strange. If the universe is only 13.8 billion years old, shouldn't we only be able to see objects that are at most 13.8 billion light-years away? The reason we can see farther is because the very fabric of space itself has been expanding throughout the entire history of the universe. The distant galaxies that emitted the light we see today were much closer to us when that light began its long journey. But in the billions of years that it has taken for that light to travel to us, the space between us and those galaxies has been stretching, carrying them much farther away. This expansion of space also stretches the wavelength of the light itself, a phenomenon known as cosmic redshift. The light from the most distant galaxies is so severely redshifted that it has been stretched from the visible and ultraviolet parts of the spectrum all the way into the infrared and microwave regions, which is why we need specialized telescopes like the James Webb Space Telescope to see it. But there is a profound and deeply unsettling problem with this cosmic expansion. It is not slowing down, as one might expect due to the mutual gravitational pull of all the matter in the universe. It is accelerating, driven by a mysterious and still completely unexplained, repulsive force known as dark energy. The universe is not just growing, it is growing at an ever-increasing rate. This has a dramatic and inescapable consequence. As time passes, more and more of the distant galaxies are being pushed away from us so fast that they will eventually cross our cosmic event horizon. They will be receding from us at a speed that is faster than the speed of light itself. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this horizon will never be able to reach us. They will be, in a very real sense, causally disconnected from our future. Anything that is currently beyond 46 billion light-years from us is already forever lost. And the galaxies that are currently on the edge of our observable universe will one by one follow them into the darkness, their light fading from our view, their existence erased from our cosmic reality. This is not a temporary technological problem. It is a fundamental, physical limit. Even if humanity one day masters the art of interstellar, or even intergalactic travel, even if we create spacecraft that can approach the speed of light, we will still never be able to reach these hidden, forbidden regions. The very laws of physics, the relentless, accelerating expansion of space-time itself, prevent us. This leads to one of the most profound and most tantalizing questions in all of cosmology: what lies beyond the observable universe? The simplest and most conservative answer is based on the cosmological principle, the assumption that our corner of the universe is not special, and that on the largest scales, the cosmos is homogeneous and isotropic, meaning it looks roughly the same everywhere and in all directions. If this is the case, then the universe beyond our view is likely just more of the same. An endless, and perhaps infinite, expanse of space filled with the same kinds of galaxies, stars, and planets, all governed by the same universal laws of physics. In this picture, the universe beyond our horizon is not fundamentally different from our own. It is just forever inaccessible. But there are other, more exotic and more mind-bending possibilities. Some cosmologists, working on the frontiers of theoretical physics, suggest that beyond our observable universe, the very nature of reality might be different. If the Big Bang was not a single, unique event, but was just one of many in a larger, eternal inflation process, then the universe beyond our sight could be a vast and chaotic multiverse. There could be other bubble universes, each with its own unique set of physical laws, fundamental constants, and even different numbers of dimensions. These would be separate, parallel pockets of reality, forever cut off from our own, each one a different, and perhaps wildly different. Answer to the question of what a universe can be. The question of whether our own universe is finite or infinite also has a profound bearing on what might lie beyond our horizon. If the universe is truly spatially infinite, as the current data seems to suggest, then the consequences are staggering. In an infinite universe, every possible arrangement of particles, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far, far beyond the cosmic censorship zone, there is another Earth, another you, an almost identical copy living out an almost identical life, perhaps making just one tiny, different choice at this very moment. And there are an infinite number of such doppelgangers spread out across an infinite cosmic tapestry. If, on the other hand, the universe is finite, then it might have a strange and wonderful topology, wrapping around on itself in a higher dimension. In such a universe, if you were to travel far enough in one direction, you might eventually end up right back where you started, like an ancient mariner circumnavigating the surface of a spherical Earth. And then there is the most radical and least likely possibility that beyond our universe, there is simply nothing, a true absolute void, a region where even space and time themselves cease to exist. This idea, however, contradicts much of what we have learned from quantum mechanics, which suggests that even the emptiest of space is a seething, energetic sea of quantum fluctuations. What makes the cosmic censorship zone so eerie and so philosophically profound is that we will likely never know for sure what lies beyond it. And as the universe continues its accelerating expansion, the region of space that we can access, the volume of our observable universe, is in a relative sense shrinking. The galaxies that we can see today, the most distant quasars and the most ancient protogalaxies, will eventually fade from our view, their light stretched by the expanding space into an undetectable, infinite redshift. Billions, and then trillions, of years from now. Future observers in our own local group of galaxies will look up at a sky that is almost completely dark, empty, and devoid of the rich cosmic tapestry that we are privileged to still be able to see. The grand cosmic web of galaxies will have vanished into the darkness, leaving only a small, lonely, and gravitationally bound island of stars in an infinite and seemingly empty void. The knowledge that we have so painstakingly acquired, the knowledge that we live in a vast, expanding cosmos filled with billions of other galaxies, could one day be lost, buried in the digital archives of a long-forgotten history, with no way for a future civilization to ever independently verify it. And yet, even within these profound and humbling limitations, our universe holds endless mysteries. The cosmic censorship zone is not just a physical boundary, it is a philosophical one. It is a stark and powerful reminder of the inherent limits of human knowledge. It tells us that no matter how far we look, no matter how powerful our instruments become, there will always be something just beyond our reach, some deeper and perhaps ultimate truth that we can never fully grasp. It is the final and most absolute cosmic horizon, a frontier that can never be crossed, not because we lack the technology or the will, but because the very nature of our expanding and accelerating. Reality ensures that some of its deepest secrets will forever remain hidden from our view. This is a humbling realization. We are used to thinking of science as a powerful and perhaps even omnipotent tool. A tool that can, In principle, unlock all the mysteries of the universe. But the very nature of the cosmos itself seems to be telling us that some answers will always and forever be out of our reach. This does not mean that we should stop searching. On the contrary, it makes our quest for knowledge all the more precious, all the more urgent. Every moment that we have to study the cosmos, every single photon of ancient light that we can gather, is a fleeting and irreplaceable opportunity to piece together the story of our universe before it moves forever beyond our grasp. In the end, the cosmic censorship zone is not just a physical limit, it is an existential one. It forces us to confront our own small and temporary place in an endless and endlessly shifting reality. It reminds us that there will always be things we cannot know, places we cannot visit, and mysteries we cannot solve. But perhaps, in the end, that is what makes the journey of exploration so beautiful and so profoundly human. The universe is not a puzzle for us to solve, but a poem for us to wonder at, a story for us to participate in, even as its most distant and most ancient. Chapters are slowly and inexorably drifting further and further away from our reach. The universe is a time machine. This is not a poetic metaphor. It is a literal, physical fact. Every time we look up at the night sky, we are not seeing the cosmos as it is in our present moment, but as it was in a distant and often ancient past. The farther away a galaxy is, the longer its light has taken to travel to us. And therefore, the further back in time we are looking. The light from some of the most distant galaxies has been journeying towards us for billions of years, carrying with it a ghostly, and often beautiful, image of the universe in its infancy. And here lies one of the most haunting and most profound truths about our cosmos. Some of the galaxies that we observe in the night sky, some of the very objects that we are studying with our most powerful telescopes, no longer exist. They are phantoms, cosmic ghosts, whose last dying light is only just now reaching our shores, while they themselves have already vanished. Their substance scattered, their stars extinguished, their reality dissolved into the expanding void. This eerie and deeply counterintuitive phenomenon is a direct consequence of the universe's rapid and accelerating expansion. The very fabric of space itself is stretching, and it is carrying the distant galaxies along with it, pushing them ever farther apart. For the galaxies that are relatively close to us, in our own local cosmic neighborhood, this expansion is a slow and gentle process. But for the galaxies that lie at the extreme, outer edges of our observable universe, the expansion is happening so quickly that they are, in effect, being pulled out of our reality. Their light struggling against a cosmic current that is flowing faster than the speed of light itself. This means that while we can still see the light that they emitted billions of years ago, a message from their distant past, they themselves have already crossed our cosmic event horizon, the point of no return, the boundary beyond which no new information, not a single additional photon of light, can ever reach us again. To truly grasp this strange and wonderful idea, imagine you are standing on the shore of a vast ocean, watching a boat sail away towards the horizon. As it moves farther and farther away, it will eventually reach a point where it seems to disappear from your view, not because it has ceased to exist, but because the curvature of the earth has carried it beyond the limit of your sight. Now, replace the ocean with the expanding fabric of space, and the boat with an entire galaxy. The universe is stretching so rapidly that certain very distant galaxies have already been carried beyond our cosmic horizon, never to be seen again in their present state. Their ancient light is still traveling towards us, a long and fading echo from their past. But once that final ancient light has all arrived, no more will follow. They will fade from our view, not because they have become too dim, but because they have become too distant, their light forever trapped in a space-time that is expanding too fast for it to ever reach us again. The most astonishing and most humbling aspect of this phenomenon is that there are galaxies we can see today, right now, in the images from our most powerful telescopes that have, in all likelihood, already ceased to exist in any recognizable form. Some of them may have been swallowed by supermassive black holes. Others might have been torn apart in colossal galactic collisions. And many have simply been stretched out into a thin, cold, and featureless nothingness by the relentless and accelerating expansion of space. The beautiful spiral arms, the glittering, star-forming nebulae, the vast, ordered structures that we see in these ancient images, all of this is long gone. The light that we receive from them today is their final message, their last beautiful glimpse into a vibrant existence before they vanished forever from the stage of the cosmos. One of the most famous and iconic images in the history of astronomy, the Hubble Deep Field, is a perfect illustration of this. This single, long exposure image captured the light of thousands of distant, and therefore ancient, galaxies in a tiny, seemingly empty patch of the night sky. Many of these galaxies are so far away that their light has been traveling for over 10 billion years to reach us. We are seeing them as they were when the universe was in its infancy, just a few 100 million years old. And yet, they are no longer there. The specific cosmic structures that they formed, the individual stars that they contained, and perhaps even the planets and the potential life that may have orbited within them, all of this is gone, washed away by the relentless cosmic tide of time and expansion. But their light, like a faint, beautiful echo from a long-forgotten past, is only just now reaching us, allowing us to witness them as they were, frozen forever in a single, ancient moment of time. This is a concept that is deeply difficult for our minds to wrap themselves around, because in our everyday terrestrial experience, things do not just disappear like this. When we look at an object, a tree, or a house, we have a very strong and reliable intuition that it exists, here and now, in our present moment. But the universe, on its grandest scales, does not work that way. The farther away something is, the older the image we see of it. And for the most extremely distant galaxies, we are looking so far back in time that their present state is not just unknown to us, it is, in a very real sense, unknowable. Some of them may still exist, in some transformed and evolved form, but many others are simply gone, their matter dispersed, their energy absorbed, their story concluded in the vast, silent expanse of space. What makes this cosmic vanishing act even more unsettling is that the universe's accelerating expansion is, as far as we know, an irreversible process. The galaxies that are currently teetering on the very edge of our observable universe today will, one by one, soon be lost to us forever. We will still be able to see their ancient, fading light for a while, for perhaps millions or even billions of years to come. But that light, that final ghostly message from their past, will eventually stop arriving. They will fade into a final, absolute blackness. Not because they have been destroyed in a fiery cataclysm, but because the fundamental laws of physics, the very geometry of our expanding space-time, will have made it impossible for their photons to ever reach us again. The fabric of space will have stretched so much and so quickly that they will have been in effect, completely and irrevocably erased from our reality. This means that, in a very real sense, we are living in a golden age of cosmic observation, right now. At this specific and perhaps fleeting moment in cosmic history, we have the technology to look deep into space and to see the beautiful, ghostly remnants of these ancient phantom galaxies. But in the far, far future, observers in our own galaxy will look up at a much, much lonelier universe. The distant galaxies that we marvel at today will no longer be visible. The Milky Way and its small, gravitationally bound group of neighboring galaxies will be all that remains in sight. And future astronomers, future civilizations, might never even know that the billions of other galaxies that we can still see ever existed. The record of their existence will have been lost, their light no longer able to reach us, their story erased by the expanding void. But this does not mean that these phantom galaxies are meaningless. Even though they have disappeared from the present-day universe, their ancient, ghostly light tells us a story. A crucial and irreplaceable story of the early cosmos. A story of how the first stars and galaxies formed from the primordial soup of the Big Bang. A story of how the intricate, beautiful, and complex structures of the universe evolved over billions of years. Every single ancient photon that reaches the mirror of our telescopes is a precious message from the past. A faint, beautiful whisper from a galaxy that may have been long, long gone. And these photons are precious because they allow us to piece together the history of our universe, before that history itself is lost to the inexorable forward march of time. There is also a profound and deeply human philosophical question that is hidden within this strange, cosmic reality. If we see something, but it no longer exists, did it ever really exist in the way that we intuitively understand existence? When we look at a galaxy that is 10 billion light-years away, we are seeing it as it was 10 billion years ago. But if we could somehow, magically, teleport ourselves to that location in space, right now, in our present moment, we would, in all likelihood, find nothing. The stars would be gone. The beautiful spiral structures would have changed beyond all recognition. We would be staring into an empty, dark space, or at something entirely different from what we had expected. This profound disconnect between the past image and the present reality challenges our very understanding of what the now really means. In a universe where time and space are so deeply and inextricably connected, it also raises another, equally unsettling question. How much of our own universe, our own cosmic neighborhood, has already disappeared from the view of a distant, alien observer? Just as we see the ancient, ghostly images of galaxies that no longer exist, it is entirely possible that there are other civilizations, in other distant parts of the cosmos, that are, at this very moment, looking back at our own Milky Way, but seeing it as it was billions of years ago. To them, our galaxy, our sun, our Earth, might be nothing more than a faint, ancient glimmer of light from a time long past, a beautiful and poignant relic of a universe that has already moved on without us. One day, we too, in all our complexity and our beauty, may become a phantom, a galaxy whose ancient light continues to travel outwards into the expanding void, a message in a bottle cast into a cosmic ocean. Long after we ourselves have faded from existence, the universe is a vast and endlessly mysterious place. And the phantom galaxies that haunt the lenses of our telescopes are a powerful and beautiful reminder that nothing is permanent. Everything we see, everything we know, everything we are, is temporary, a fleeting, flickering moment in the grand, and often tragic, sweep of cosmic history. And yet, in that fleeting moment, there is a profound and undeniable beauty. The very knowledge that we are witnessing something that no longer exists, something that has been lost to the relentless, cosmic tide, makes every image, every observation, every single precious photon of ancient light all the more meaningful. It reminds us that the universe is always changing, always evolving, and that we are incredibly, wonderfully, and perhaps even tragically lucky to be here, now, to glimpse even the tiniest fraction of its magnificent and ultimately fleeting story, before it, too, fades forever, beyond our reach. The universe hides its deepest and strangest mysteries in the darkness. And among the most enigmatic of these dark mysteries is the idea of primordial black holes, hypothetical and ghostly, remnants from the very first, fiery moments after the Big Bang. If they exist, they are not like the black holes we know, the stellar mass behemoths that are formed from the violent, explosive deaths of massive stars. These would be something entirely different, something more ancient, more fundamental, more elusive. They would be black holes formed not from the collapse of pre-existing matter, but from the raw, untamed, and incredibly dense energy fluctuations of the newborn universe itself. But here lies the profound and deeply frustrating paradox of their existence if they are real. They are so small, so dark, and so perfectly hidden in the vast, expanding fabric of space that we may never, ever be able to find them. Primordial black holes are believed to have formed in the very first, infinitesimal fractions of a second after the universe came into existence. At that time, the cosmos was an unimaginably hot and dense place, a chaotic, roiling sea of pure energy and fundamental particles. In this primordial soup, tiny, random, quantum fluctuations slight and unavoidable. Imbalances in the density of energy could have been so extreme that they caused certain super-dense regions of space to spontaneously collapse in on themselves, forming minuscule black holes. Unlike the black holes that are formed from the collapse of dying stars, which must have a mass of at least a few times that of our Sun, these primordial black holes could, in theory, have any mass. They could be as small as a single atom, or as massive as a large planet, their size depending entirely on the scale and the intensity of the density fluctuation from which they were born. Theoretically, these ancient primordial black holes could have survived for the entire 14 billion-year history of the universe, drifting silently and invisibly through the cosmos. Perfect, dark relics of the first moment of creation. But their very nature, their small size and their lack of any significant interaction with their surroundings makes them nearly impossible to detect. Unlike the stellar mass or supermassive black holes that we can observe, which are often surrounded by bright, glowing accretion disks of gas and dust that is being pulled into them, these primordial black holes would be, for the most part, completely isolated, wandering through the vast, empty voids of the universe like silent, cosmic ghosts. If they are small enough, they would slowly emit a faint thermal radiation, a process known as Hawking radiation, and would, over immense cosmological timescales, eventually evaporate completely. But if they are just a little larger, say with the mass of a small asteroid, they could persist indefinitely, their existence completely invisible to our current and perhaps any future technology. For decades, scientists have been searching for any evidence, however indirect, of these ancient, primordial black holes, but finding them is like looking for a single dark grain of sand in an infinite dark desert. They do not emit any detectable light. They do not interact with their surroundings in any obvious way. And they may be far too small to have any significant gravitational influence on the stars and galaxies around them. The only real hope of detecting them lies in their potential. Gravitational effects. They could, in theory, act as gravitational lenses, their tiny but intense gravity bending the light of a distant star as they pass in front of it, creating a brief and characteristic brightening event. Or they could subtly affect the movement of the large-scale cosmic structures that we can observe. But even these potential clues are incredibly faint, almost imperceptibly so, when set against the vast and often noisy backdrop of the cosmos. One of the most intriguing and most exciting ideas about primordial black holes is that they could be a leading candidate for the mysterious and still completely unidentified dark matter, the invisible gravitational substance that seems to make up the vast majority of the matter in the universe. Dark matter is known to us only through its gravitational influence. It has weight, it pulls on galaxies, it shapes the large-scale structure of the cosmos, but it emits no light, no radiation, no signal of any kind. Could it be that this hidden gravitational mass that has eluded scientists for so long is, in fact, a vast cosmic population of ancient primordial black holes? Some researchers believe that this is a real and even a likely possibility, but there is, as yet, no direct experimental evidence to support it. If primordial black holes are indeed the source of dark matter, then they are even more elusive and more profoundly mysterious than we ever imagined. They would be everywhere, all around us, making up the very gravitational scaffolding of our own galaxy. And yet, they would remain completely and utterly unseen. The frustrating and beautiful reality is that even if they do exist, we may never be able to definitively prove it. They are too small to be observed directly. They are too dark to emit any detectable radiation. And they are too isolated to reveal themselves through their interactions with the world we can see. Even our most advanced telescopes and our most sensitive gravitational wave detectors may not be enough to ever confirm their presence. We might only ever be able to infer their existence from a collection of subtle, indirect clues, a slight, unexplained anomaly in the motion of a distant galaxy, a brief and unrepeatable flash of lensed light from a background star, a tiny and statistically ambiguous distortion in the faint, ancient glow of the cosmic microwave background. There is a cruel and beautiful irony in this. The very nature of primordial black holes, their ancient origin and their profound physical simplicity, makes them one of the most compelling and most elegant ideas in all of modern physics. And yet, at the very same time, it may place them forever beyond the reach of our direct, empirical verification. They could be everywhere, hidden in the silent, dark void of space. And yet, we might never be able to prove that they are real. The universe, it seems, does not always reveal its secrets easily, some of its deepest and most fundamental. Questions may remain forever unanswered, not because they have no answers, but because the answers are too well and too perfectly hidden for us to ever find them. And yet, the possibility of primordial black holes, the dream of finding these ancient cosmic relics, continues to haunt us, to inspire us, to push us forward in our quest for understanding. If they do exist, then they are the oldest and most fundamental structures in the entire universe, predating the formation of galaxies, of stars, and even of the first stable atoms. They are living, breathing fossils from a time before anything we would recognize as existence had even begun. And if they do not exist, then we are left with another, equally profound, mystery. What happened to the extreme, primordial density fluctuations that our theories predict should have formed them? Why did the early universe evolve in such a way that it so perfectly and so elegantly avoided their creation? Either way, whether they are out there in the darkness or not, the search for primordial black holes forces us to confront the very limits of what we can know, of what we can see, of what we can ever hope to understand. The universe is vast, and some of its deepest and most beautiful Secrets may remain hidden from us forever, lost in the deep, profound, and eternal silence of space. The solar system that we see today, with its familiar and largely stable arrangement of planets and moons, is a product of billions of years of cosmic evolution. It is a system that has been shaped by violent collisions, by graceful planetary migrations, and by the relentless and patient pull of gravity. When we look up at the familiar, comforting face of our own moon in the night sky, or when we observe the beautiful, intricate dance of the moons of Jupiter and Saturn through our telescopes, we are only seeing a small and perhaps fortunate fraction of what once existed. The solar system was not always as it is now. It was once a far more chaotic, more dynamic, and more violent place, a place where countless, and now forgotten, moons were formed, only to be torn apart, to be ejected into the cold, deep space, or to be lost forever to the dark and silent void. These lost moons, these ghostly and often tragic remnants of a time when our solar system was still young, wild, and unstable, may still exist somewhere out there, hidden beyond the reach of our current instruments, drifting alone and silently in the eternal darkness. Some of them may have been completely destroyed in violent and cataclysmic impacts, their shattered remains now forming the rings of the giant planets or the scattered debris of the asteroid fields. Others may have been thrown out into the distant and largely unexplored reaches of the Oort cloud, a vast, spherical, and icy region that marks the very edge of our solar system. A place where they would remain frozen, undisturbed, and nearly impossible for us to ever detect. And some, the most unfortunate of all, may have escaped the gravitational pull of our sun entirely, becoming rogue moons, wandering aimlessly and eternally through the vast, cold, and lonely expanse of interstellar space, untethered from any star, and destined to drift forever in the endless silent night. In the earliest days of our solar system, more than 4.5 billion years ago, there were no clearly defined planets, no stable, predictable orbits, no familiar cosmic clockwork. Instead, there was a vast, swirling, and turbulent disk of gas, dust, and debris surrounding our young, and still forming, sun. And as this primordial material slowly began to clump together under the influence of gravity, the first infant planets, the protoplanets, and their first nascent moons began to form. But this was not a peaceful or a gentle process. It was a time of cosmic violence, a time of immense and often world-shattering collisions. Newly formed planets and moons were constantly smashing into each other, their surfaces being reshaped, their orbits being altered, or their very existence being snuffed out in a final, fiery instant. Some of these impacts were so powerful, so cataclysmic, that they changed the entire course of our solar system's history. The very moon that we see in our sky today is thought to have been formed from just such an event, a massive and glancing collision between the early, molten Earth and a Mars-sized protoplanetary body. An impact that would have ejected a vast cloud of molten rock and debris into orbit, which then, over time, coalesced to form our familiar and beautiful lunar companion. And if this could happen to our own Earth, then it is almost certain that the other planets in our solar system also had a long and often violent history of moon formation, a history where moons were formed, were destroyed, and were replaced multiple times throughout the chaotic youth of our cosmic neighborhood. The giant, gas planets of our outer solar system, Jupiter and Saturn, have dozens of moons today, a beautiful and complex family of orbiting worlds. But in the distant past, they may have had even more. These gas giants are so incredibly massive that they have a powerful gravitational reach, an ability to capture passing objects and to pull them into orbit. This means that many of their current moons were likely not formed alongside them, but were stolen from the asteroid belt, or were captured from the icy debris of the outer solar system. But just as these giant planets can capture new moons, they can also lose their old ones. When planets migrate, when they slowly shift their positions in the solar system due to the complex gravitational interactions between them, they can disrupt everything around them. A moon that was once in a safe and stable orbit can suddenly find itself on a new and highly elliptical path. A path that could lead it to collide with another moon, to crash into its host planet, or to be flung with immense force out of the planetary system entirely. Jupiter and Saturn, our solar system's two gravitational behemoths, likely underwent significant periods of migration in their early histories. A chaotic cosmic dance that would have reshaped the entire architecture of the outer solar system, and would have, in all likelihood, resulted in many of their original primordial moons being lost in the process. Some of these lost, ancient moons may still be out there, hiding in the farthest and coldest reaches of our solar system, far beyond the orbit of Neptune, beyond the Kuiper Belt, in the vast and largely mysterious realm of the Oort cloud. The Oort cloud is a hypothetical and almost unimaginably large, spherical cloud of icy bodies that is thought to surround our solar system, at a distance of nearly a light-year from the Sun. It is believed to be the ancient and largely undisturbed reservoir of long-period comets, those icy and beautiful visitors that occasionally get nudged from their distant orbits and fall inwards towards the Sun, their long, ghostly tails of fleeting and beautiful, reminder of the vast, cold, and ancient history of our cosmic home. And if these smaller, icy bodies, these comets, can survive in the Oort cloud for billions of years, then it is entirely possible that some of our solar system's lost, ancient moons also ended up there, trapped forever in the faint, gravitational influence of our Sun, but too far away, too cold, and too dark for us to ever see them. These would be frozen and lifeless worlds, locked in the deep, silent space of the outer solar system, their surfaces preserving a perfect and eternally unchanging record of the violent and chaotic youth of our cosmic neighborhood. And even if they do exist, finding them would be a task of almost unimaginable difficulty. They would be too dark and too distant to be observed directly with any of our current or even near-future telescopes. Other, and perhaps more numerous, of these lost moons may have faced an even more dramatic and more final, fate complete, and total ejection from the solar system itself. If a moon, during a close gravitational encounter with a massive planet, was thrown outwards with enough force, with enough velocity, it could have escaped the gravitational pull of our Sun entirely, becoming a rogue object, a lonely and untethered wanderer, drifting freely and silently through the vast, dark, and empty expanse of interstellar space. Scientists in recent years have already discovered the existence of rogue planets, planets that do not orbit any star, but instead move, dark and alone, through the galaxy. And if rogue planets exist, then it is almost certain that rogue moons must also exist. Some of them may have been born in the turbulent, star-forming nurseries of our galaxy, but many of them, perhaps even billions of them, may have once been a part of a solar system just like our own, a moon that was torn from its home by the chaotic, gravitational dance of its planetary siblings. And some of them, it is almost certain, may have once been our own, forgotten and long lost, cosmic neighbors without a nearby star to warm them, to illuminate them. These lost, rogue moons would be almost completely invisible, impossible to detect with even our most advanced and most powerful telescopes. They could pass by other solar systems, moving silently and darkly through the void, never to be captured by the gravity of another planet, forever alone in the endless cosmic night. And if any of these moons once had the potential for life, if they had subsurface oceans of liquid water, or the right chemical ingredients for biology, their ejection into the cold, deep space would have sealed their fate. Without the gentle, life-giving warmth of a star, any potential for life would have been frozen in an instant, preserved forever in the deep, icy shell of a moon that would never again see the light of day. The thought of such worlds, of places that once held the potential for oceans, for weather, for dynamic, geological activity, now drifting, dark and aimlessly, through the vast and lonely void, is a profound and deeply haunting reminder of just how fragile and how precious celestial bodies can be. Unlike the massive planets, which have a strong and stable gravitational hold on their orbits, the smaller moons are far more easily lost, making them some of the most transient and most vulnerable objects in the entire universe. The lost moons of our early solar system are not just a romantic and tragic relic of our cosmic past. They are also a crucial and largely missing piece of the puzzle of how planetary systems form and evolve. By studying the moons that remain, the ones that have survived the long and often violent history of our solar system, scientists can begin to infer what might have happened to those that were lost. The deep, ancient craters on our own moon, the irregular and often chaotic shapes of the asteroid belts, the strange and highly inclined orbits of the small, icy bodies in the outer solar system. All of these are clues, are fossils, that point to a history that is far more violent and far more complex than the serene and seemingly peaceful solar system we see today. If we ever develop the technology to send spacecraft on long, multi-generational journeys to explore the vast and largely unknown reaches of the Oort cloud, we may one day find direct and stunning evidence of these lost ancient moons. Perhaps we will even find the frozen and perfectly preserved remnants of worlds that were once a part of our own familiar cosmic neighborhood. But for now, these lost moons remain a deep and beautiful mystery, hidden forever beyond our reach. Some may still be orbiting, dark and unnoticed, in the vast, cold expanse of the outer solar system. Some may be buried, deep and forever, in the distant, icy graveyard of the Oort cloud. And many, many others have likely left us forever, drifting, dark and alone, in the endless, silent emptiness between the stars. We may never know their names, we may never see their shapes, we may never learn their stories, but they're silent and ghostly. Absence is a powerful and deeply poignant reminder of the profound and often tragic impermanence of celestial bodies, a reminder of the way that the cosmos is constantly shifting, constantly changing, and constantly reshaping itself in a beautiful and often violent and eternal cosmic dance. The universe is full of forgotten worlds, and among them, silent and unseen, are the lost, lonely moons of our own, ancient past, silent travelers, forever unremembered, but forever a part of the grand and ongoing story of our solar system, The universe is in constant and often dramatic motion. It is a vast and dynamic expanse, a place where entire galaxies, each containing hundreds of billions of stars, are not just floating aimlessly in the void, but are drifting and often racing through space, bound together by the invisible and powerful threads of gravity. Our own Milky Way galaxy, along with its retinue of smaller satellite galaxies, is not a static island universe. It is part of a much larger cosmic flow, a grand celestial river of galaxies that is being pulled with immense and inexorable force towards something massive, something mysterious, something that we cannot even directly see. This unseen and incredibly powerful gravitational force is known as the Great Attractor, a vast and diffuse gravitational anomaly that is so powerful, so massive, that it is drawing entire clusters of galaxies, including our own, towards it at almost unimaginable speeds. And yet, for all of its profound and universe-shaping influence, we cannot see it. The Great Attractor lies hidden, shrouded, and tantalizingly behind the thick and obscuring veil of our own galaxy's dusty, star-filled plain, a region of the sky known as the zone of avoidance, making it one of the greatest and most frustrating mysteries in all of modern cosmology. To understand the true significance and the deep mystery of the Great Attractor, we must first zoom out and look at the large-scale structure of the universe itself. Galaxies are not scattered randomly and uniformly throughout space. Instead, they are arranged in a vast and beautiful cosmic web, a network of immense, interconnected filaments of galaxies surrounding vast and largely empty cosmic voids. Our own Milky Way is a member of a small and relatively modest collection of about 50 galaxies known as the Local Group. And this local group is itself just a small suburban outpost on the edge of a much, much larger structure, a massive supercluster of galaxies known as the Laniakea supercluster. This cosmic behemoth, whose name means immeasurable heaven in Hawaiian, contains over 100,000 galaxies, all gravitationally bound and all moving, more or less, in the same general direction through space. And that direction, as astronomers have painstakingly discovered by measuring the subtle motions of thousands of galaxies, is directly towards the mysterious and unseen Great Attractor. The gravitational pull of the Great Attractor is enormous. Our own galaxy, the Milky Way, is being pulled towards it at a staggering speed of about 600 kilometers per second, which is over 1.3 million miles per hour. And everything else in our cosmic neighborhood, including the entire massive Virgo cluster of galaxies and all the other nearby galaxy groups, is also moving in the same general direction, all caught in the same powerful gravitational current. This coherent, large-scale flow of galaxies strongly suggests the presence of an immense and previously unknown concentration of mass, a mass that is far, far larger than anything in our immediate cosmic vicinity. And yet, when astronomers have tried to pinpoint the source of this immense gravitational pull, they have run into a formidable and deeply frustrating problem. The center of this gravitational anomaly is located in a part of the sky that is almost completely obscured by the dense and intervening clouds of gas, dust, and stars of our own Milky Way's galactic plane. This region, the zone of avoidance, acts like a thick cosmic fog, blocking our view and making direct optical observations of what lies beyond it almost completely impossible. For decades, scientists have struggled to understand what lies behind this cosmic barrier. If the Great Attractor is so incredibly massive that it can influence the motion of entire superclusters of galaxies, then why can we not see it? The answer, it seems, lies in the way that mass is distributed in the universe, unlike a single, compact object, like a supermassive black hole or a dense, collapsed star. The Great Attractor is not a single, well-defined body. It is, instead, a vast and highly diffuse region of space, a place where the density of galaxies and of the invisible dark matter that surrounds them is particularly high. It is the combined and immense gravitational pull of all these individual and often faint structures that creates the powerful and large-scale gravitational attraction that we observe. But because this mass is spread out over such a vast and distant region of space, it does not emit a single concentrated point of light, like a bright star or a quasar would, making it even more difficult to detect and to study. Despite these immense challenges, astronomers, with their characteristic ingenuity and perseverance, have found clever and indirect ways to study the Great Attractor. By using radio waves and X-ray telescopes, which can penetrate through the obscuring dust and gas of the Milky Way's plane far more effectively than visible light, scientists have been able to detect some of the galaxies and galaxy clusters that reside within this hidden cosmic region. And these observations have revealed a tantalizing and even more complex picture. They suggest that the Great Attractor itself is not the final, ultimate source of the gravitational pull, but is, in fact, just one part of an even larger and even more massive structure, a colossal supercluster of galaxies known as the Shapley supercluster. The Shapley supercluster is one of the most massive and most densely populated concentrations of galaxies in the entire observable universe. It contains thousands of individual galaxies, all packed together in a relatively small volume of space, and it is now thought to be the true primary source of the immense gravitational pull that is affecting our entire local region of the cosmos. But the mystery does not end there. Even beyond the immense gravitational influence of the Shapley supercluster, astronomers have found evidence that our entire local supercluster, Laniakea, is being influenced by another, even more distant and even more powerful cosmic force. This has led to the discovery of what is known as the dipole repeller, a vast and largely empty cosmic void that is, in effect, pushing us away. While the Great Attractor and the Shapley supercluster are pulling us forward, the cosmic motion of our galaxy, it seems, is the result of a complex gravitational tug-of-war, a delicate and beautiful dance between the immense, attractive forces of the great cosmic structures on one side and the subtle, repulsive forces of the great cosmic voids on the other. This suggests that the universe is shaped by even larger and even more complex forces than we had ever imagined, forces that extend far beyond what we can currently, and perhaps ever, directly observe. One of the most intriguing and most important aspects of the mystery of the Great Attractor is the central and largely unknown role of dark matter. The ordinary baryonic matter that makes up the stars, the planets, the gas, and the dust that we can see accounts for only a small and almost insignificant fraction of the universe's total mass. The vast majority of the matter in the cosmos, about 85% of it, is composed of a mysterious and completely invisible substance that we call dark matter. We know it is there because we can see its immense gravitational effects. But we do not know what it is, and it is entirely possible, and even likely, that the immense gravitational pull of the Great Attractor is not just the result of the visible baryonic galaxies that we can, with great difficulty, detect within the zone of avoidance. It is also, and perhaps primarily, the result of a vast and completely unseen concentration of this mysterious dark matter. If this is the case, then our inability to directly and clearly observe the Great Attractor is not just due to the obscuring fog of our own Milky Way, but also, and more fundamentally, because the vast majority of its mass is made up of a strange and invisible substance that we still do not fully understand. As our technology continues to advance, astronomers are developing new, and ever more powerful, ways to peer into the hidden and forbidden corners of our universe, new and more sensitive. Infrared and radio telescopes are continuing to provide us with clearer and more detailed glimpses of the galaxies that lie within the zone of avoidance and future. Next-generation space missions may offer even deeper and more profound insights. The Vera C. Rubin Observatory, a massive new telescope that is set to begin its survey of the southern sky in the coming years, will provide an unprecedented and wide-field map of the universe, and it may uncover new and crucial clues about the nature of the Great Attractor and its place in the grand cosmic structure. Similarly, the successors to the James Webb Space Telescope could help us to refine our understanding of this profound gravitational enigma. But for now, the Great Attractor remains one of the most intriguing, most elusive, and most beautiful of all cosmic mysteries. We know it is there. We can feel its inexorable gravitational pull, and yet we cannot fully or clearly see it. It is a powerful and deeply humbling reminder that despite all the remarkable and often stunning progress we have made in our quest to understand the universe, there are still vast and powerful forces that are shaping our cosmic destiny, forces that remain, for now, completely hidden from our view. Perhaps one day, with the right new tools and with the right new theoretical insights, we will finally be able to unveil the true and full nature of the Great Attractor and to understand its central and profound place in the grand and beautiful structure of the cosmos. But until then, we continue to race towards it at over 1,000,000 miles per hour, bound by the silent and invisible threads of gravity that so beautifully and so mysteriously weave our entire universe together. In the vast and often bizarre menagerie of the cosmos, among all the strange and wonderful particles that make up our reality, there are some that are so elusive, so ghostly, so profoundly interactive, that they can pass through entire planets, through stars, through galaxies, without ever leaving a single detectable trace. These are the neutrinos, the little neutral ones, the shyest and most mysterious of all the known fundamental particles. But there may be an even stranger and even more elusive version of these particles, a hypothetical entity that is so undetectable, so intangible, so completely and utterly disconnected from our familiar physical world that it could be all around us, passing through us and shaping the very evolution of our universe, without us ever being able to directly know it. These are the sterile neutrinos, the true and ultimate ghost particles of the universe. And if they exist, they may hold the key to some of the deepest and most profound mysteries in all of modern physics. To understand the strange and wonderful nature of sterile neutrinos, we must first look at their more familiar and already quite strange relatives, the three known flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These neutrinos are produced in incredible abundance throughout the entire universe, emerging from the fiery nuclear reactions in the hearts of stars, from the cataclysmic, explosive deaths of supernova, and even from the decay of radioactive elements here on Earth. Every single second, trillions upon trillions of neutrinos, mostly from our own sun, are passing through your body without you ever noticing, without them ever leaving a single discernible trace. This is because neutrinos interact with other matter only through the weak nuclear force, one of the four fundamental forces of nature, and this force, as its name suggests, is incredibly weak. A neutrino could travel through a light year of solid lead without ever hitting a single atom. And yet, for all their near invisibility, physicists with their characteristic ingenuity, have been able to detect and to study these neutrinos. They have built giant and often beautiful underground detectors, massive tanks filled with thousands of tons of ultra-pure water or liquid argon, buried deep beneath mountains to shield them from the confusing noise of other, more interactive, cosmic rays. And in these vast, silent chambers, the rarest of the rare, quantum interactions between a neutrino and an atom can be detected, leaving behind a faint and beautiful trace of its ghostly passage. But sterile neutrinos, if they exist, would be something else entirely. Unlike the three known types of neutrinos, which all participate in the weak nuclear force, sterile neutrinos are theorized to not interact with ordinary matter at all, not even through this incredibly weak force. The only influence they would have on the universe would be through the universal and all-pervasive force of gravity. This means that even our most advanced and most sensitive neutrino detectors would be completely and utterly blind to them. If sterile neutrinos exist, they could be the most elusive and most mysterious form of matter in the entire universe, hidden from us in plain sight. Their presence felt only through the subtle and often ambiguous pull of their collective gravitational weight. The idea of the sterile neutrino, as strange as it may sound, is not just a wild, ad hoc speculation. It arises naturally from several deep and as yet unresolved mysteries in our current understanding of physics. One of the biggest of these puzzles is the very fact that neutrinos have mass at all. In the standard model of particle physics, the incredibly successful theory that describes all the known fundamental particles and their interactions, neutrinos were originally thought to be completely massless, like the photon, but a series of brilliant and Nobel Prize-winning experiments in the late 1990s and early 2000s showed that neutrinos do, in fact, have a tiny but non-zero mass. This was a revolutionary discovery, as it was the first direct experimental evidence for physics beyond the standard model. And one of the most elegant and most popular theoretical explanations for the origin of neutrino mass is the seesaw mechanism, a model that requires the existence of a new and much heavier type of neutrino that does not interact through the weak force. This would be the sterile neutrino, another and more direct clue that points to the possible existence of sterile neutrinos comes from a series of strange and still unexplained anomalies in the data from several different neutrino experiments. Experiments like the liquid scintillator neutrino detector at Los Alamos in the 1990s and the more recent Mini-Boone experiment at Fermilab have observed an excess of certain types of neutrino oscillations, the process by which neutrinos can change their flavor as they travel through space that cannot be easily explained by the three known types of neutrinos alone. One possible and very exciting explanation for these anomalies is that there is a fourth, and as yet undiscovered, type of neutrino, a sterile neutrino that is mixing with the other three, creating a new and more complex pattern of oscillations. And if sterile neutrinos exist, they could also help to solve one of the greatest and most enduring mysteries in all of cosmology, the nature of dark matter. Dark matter, as we have seen, is the invisible gravitational substance that makes up about 27% of the total mass energy content of the universe. We know it is there, but we do not know what it is. Some theories propose that sterile neutrinos, if they have the right mass, could be a form of warm dark matter, a candidate that could explain some of the subtle discrepancies between the predictions of the standard cold dark matter model and the observed structure of galaxies on small scales. If this is the case, then the universe is filled with a vast and ghostly sea of these sterile neutrinos. their collective gravity shaping the evolution of the cosmos, while they themselves remain almost completely and utterly undetectable. The challenge, of course, the great and deeply frustrating challenge, is to find a way to prove that these ghostly, sterile neutrinos actually exist, because they do not participate in the weak nuclear force. Our current direct detection methods are completely useless, so scientists have been forced to get creative, to look for the subtle, indirect signatures of their existence. The search for anomalous neutrino oscillations continues, with new and more powerful experiments, like the Deep Underground Neutrino Experiment, which will send a beam of neutrinos 800 miles through the Earth from Fermilab in Illinois to a massive underground detector in South Dakota, hoping to measure the properties of neutrino oscillations with unprecedented precision. Other experiments are looking for the faint, X-ray signals that could be produced by the very slow decay of sterile neutrinos over cosmological timescales. And some are even looking for the subtle, gravitational effects that a large population of sterile neutrinos could have on the structure of the early universe, as seen in the faint, ancient light of the cosmic microwave background. But so far, no definitive and universally accepted evidence has been found. The implications of discovering a sterile neutrino would be truly enormous. It would not just force us to rewrite the textbooks of particle physics, it could also fundamentally reshape our understanding of the universe's composition, its history, and its evolution. It might even provide a crucial clue to another deep and related mystery, the matter-antimatter asymmetry of the universe. According to our current understanding of physics, the Big Bang should have produced matter and antimatter in almost exactly equal amounts, and when matter and antimatter meet, they annihilate each other in a flash of pure energy. So, the universe should be filled with nothing but a sea of radiation. But it is not. It is filled with matter, with us. Something, in the first, fiery moments of creation, must have tipped the cosmic scales, creating a tiny but crucial excess of matter over antimatter. The leptogenesis scenario, a leading theoretical explanation for this asymmetry, proposes that the decay of heavy, sterile neutrinos in the early universe could have created this imbalance, a process that is intimately linked to the same seesaw mechanism that gives the light neutrinos their mass. But what if sterile neutrinos are never found? What if they exist, but are truly and fundamentally undetectable? They would remain forever beyond our reach, a ghostly and unprovable presence, their influence on the cosmos felt, but never directly seen. This would be one of the most frustrating and most humbling possibilities in all of physics. A fundamental and perhaps even crucial particle that shapes the very nature of our reality. But that can never be conclusively and definitively proven to exist. It would be like knowing that there is a hidden and powerful force that controls the destiny of the universe, but never being able to touch it, to see it, or to measure it in any way. And yet, the history of science has shown us, again and again, that what seems undetectable today may become observable with the new and often unpredictable technologies of the future. When the neutrino itself was first theorized by Wolfgang Pauli in the 1930s, many physicists, including Pauli himself, believed that it would never be detected, as it was thought to interact far too weakly with matter. But decades later, clever and patient, experimentalists built the giant underground detectors that proved that neutrinos were real. Perhaps one day, a new and even more clever breakthrough in physics will allow us to indirectly but unambiguously confirm the existence of sterile neutrinos, unlocking one of the final and most profound secrets of the cosmos. But until then, sterile neutrinos will remain a beautiful and deeply tantalizing possibility, a ghostly whisper in the grand, cosmic symphony, a silent and powerful force that may exist forever, just beyond our grasp, whether they are the key to the mystery of dark matter, the answer to the puzzle of cosmic asymmetry, or merely a phantom, a beautiful and ultimately incorrect prediction that will lead us in new and even more interesting directions. They're profound and beautiful. Mystery continues to haunt the very frontiers of modern physics. For as long as humans have gazed up at the night sky, for as long as we have been conscious, questioning beings, we have wondered where everything came from. The prevailing and remarkably successful scientific theory is that our universe began approximately 13.8 billion years ago, in a hot, dense, and incredibly energetic event that we call the Big Bang. Everything we see today, the stars, the galaxies, the planets, and even the very fabric of space and time itself was born from this single, momentous, and transformative moment of creation. But this powerful and well-tested explanation inevitably raises a deeper and perhaps even more profound question: what came before the Big Bang? Was there a time before time? Did our universe simply and miraculously emerge from a state of absolute nothingness? Or has the universe, in some strange and perhaps unrecognizable form, always existed? And if it has, are all the past, and perhaps infinite, versions of our reality lost to us forever, their histories, their stories, their very existence, erased like fleeting, ephemeral footprints on a vast and timeless cosmic shore? One of the most perplexing and most humbling ideas in all of modern physics is that the very concept of time itself may have begun with the Big Bang. According to Einstein's general theory of relativity, space and time are not separate, independent entities. They are two inseparable aspects of a single, unified, four-dimensional fabric that we call space-time. And if the universe, if space, had a beginning, then it seems that time itself must have also had a beginning. This means that asking the question, what came before to the Big Bang, might be like asking the question, what is north of the North Pole? It may be a question that is not just unanswerable, but is, in a fundamental, logical sense, meaningless. However, many physicists and many philosophers are not satisfied with this seemingly simple and somewhat dismissive answer. If the universe and time itself simply sprang into existence from nothing, then what determined the specific laws of physics that govern it? Why does the universe exist at all, with all its beauty and its complexity, instead of simply remaining in a state of eternal, empty, and timeless void? These deep and perhaps unanswerable questions have led scientists to explore other, more exotic and more mind-bending possibilities, including the idea that the universe is, in fact, eternal, and has always existed in some strange and cyclical form. One of the most popular and most elegant of these alternative theories is the idea of a cyclic universe. Instead of beginning from a state of absolute and singular nothingness, the universe may go through an endless and perhaps eternal series of expansions and contractions, much like a great cosmic heartbeat. In this model, the Big Bang was not the true, absolute beginning of all things, but was merely the latest rebirth of the universe, before our current expanding universe. There may have been another, and perhaps very different, universe. A universe that expanded, that cooled, that formed its own stars and galaxies, and that then, eventually, collapsed back in on itself in a fiery, big crunch, a cataclysmic event that then, in turn, gave rise to the Big Bang of our own. cosmic eon. And if this process has been happening forever, then the universe has no true, single starting point. It has only an endless and beautiful cycle of creation and destruction, of death and rebirth. But if the universe is truly cyclical, if it has gone through a potentially infinite number of past iterations, then what happened to all of those previous universes? Why do we have no memory, no record, no physical evidence of their existence? The answer, it seems, may lie in the relentless and unforgiving arrow of time, the second law of thermodynamics. With each new cycle of the universe, the total entropy, the total amount of disorder, should increase. This means that even if a new universe is born from the ashes of the old, it will not be an exact copy. The information from the previous cycle, the detailed record of its history, its structure, its life, is effectively lost, scrambled, and erased in the fiery and high entropy crucible of the bounce from a big crunch to a big bang. This means that even if there have been an infinite number of past universes, they have each, in their own turn, left no discernible and recoverable trace behind. Everything that came before us in this cyclic picture has been effectively and completely erased, making it impossible for us to ever recover any direct and detailed knowledge of what happened before our own local Big Bang. Another, and equally profound, possibility is the idea of the multiverse. Instead of a single universe that cycles through different sequential stages, there may be an infinite and coexisting number of other parallel universes, each with its own unique beginning, its own unique history, and its own unique set of physical laws. In some versions of this theory, like the eternal inflation model, new bubble universes are constantly being born in a vast and ever-expanding cosmic landscape, each one emerging from a random quantum fluctuation or from a localized, phase transition-like expansion of space-time. If this is true, then what came before our own Big Bang was not a single previous universe, but a vast and complex multiversal reality, a cosmic foam where every possible and conceivable reality exists somewhere in its own self-contained bubble. But even the multiverse does not fully or satisfyingly answer the question of an infinite past. If there are many, and perhaps an infinite number of other universes, then where did they come from? Has the multiverse itself always existed, or did it, too, have a beginning? Some scientists and philosophers have proposed that the very concept of time itself may not be a fundamental aspect of reality, that what we experience as the linear to forward flow of time is just a human, and ultimately illusory, perception of a much deeper and perhaps timeless reality. If time is an emergent property rather than a fundamental feature of the universe, then the very question of what came before the Big Bang may not have a meaningful or even a sensible answer at all. The universe, in this sense, may simply be a timeless and eternal mathematical structure without a beginning or an end. However, there is one formidable and perhaps insurmountable problem that remains, regardless of which of these grand cosmological stories we choose to believe, and that is the nature of the Big Bang itself. If we could somehow, with our theories and our instruments, peer back far enough into the past, beyond even the first fleeting moments of our universe's existence, we might be able to find some direct and unambiguous clues about what came before, but the problem is that our current and remarkably successful physical theories, the theories of general relativity and quantum mechanics, break down at the very moment of the Big Bang. The extreme and infinite density and energy of the early universe create a singularity, a point in space-time where our laws of physics cease to have any meaning, where our equations give nonsensical, infinite answers. This singularity acts like a great and impenetrable cosmic curtain, blocking us from ever being able to see or to know anything that lies beyond it, unless we can somehow develop a new and more complete theory of physics, a theory of quantum gravity that can describe what happens at and beyond the singularity. The ultimate past, the time before the Big Bang, may forever remain a deep and beautiful mystery, despite these immense and perhaps even fundamental challenges. Some scientists believe that we may still be able to find some indirect and circumstantial evidence of a time before the Big Bang. If the universe is truly cyclical, there might be subtle and almost imperceptible imprints of the previous universes left behind in the faint, ancient glow of the cosmic microwave background. Some researchers have suggested that certain large-scale circular patterns in the temperature of this radiation could be the ghostly and beautiful remnants of the black hole collisions that occurred in the previous cosmic eon. So far, no such conclusive evidence has been found. Similarly, if the multiverse is real, then the collision of our own bubble universe with another could have left a cosmic bruise, a subtle and detectable distortion in the distribution of galaxies on the largest scales. But what if we will never, ever truly know the answer? What if the past is, in fact, lost to us forever, hidden behind an impenetrable and eternal wall of cosmic history? If that is the case, then the true nature of the infinite past may remain one of the greatest and most beautiful of all unanswered questions in science. We may live in a universe that, by its very nature, erases its own history. A universe that is constantly being reborn. A universe that leaves us with only the fleeting and beautiful present moment, and a deep and enduring mystery that stretches forever and silently into the endless and unknowable past. And still, the search for answers continues. Every new discovery, every new theory, brings us just a little bit closer to understanding the true and ultimate origins of our own cosmic reality. And perhaps one day, a new and brilliant breakthrough in physics will reveal a deeper and more profound truth about the nature of space, of time, and of existence itself. But until then, we are left to wonder, was there something before the Big Bang? Or has the universe, in some strange and beautiful and perhaps cyclical form, always been stretching back forever into an infinite and timeless past that we can never, ever truly grasp? The search for intelligent life beyond our own small and fragile planet is a question that has haunted the human imagination for centuries. With an estimated 2 trillion galaxies in our observable universe, each filled with hundreds of billions of stars, and with the recent discovery of countless and often Earth-like planets orbiting those stars, it seems almost a statistical impossibility that we are alone. The sheer, overwhelming numbers suggest that life, and perhaps even intelligent and technological life, should have arisen many, many times throughout the long and often violent history of the cosmos. And yet, when we turn our radio telescopes to the heavens, when we listen for the faint and telltale whispers of a distant alien civilization, the universe is eerily and profoundly silent. We have been listening with ever-increasing sensitivity for decades now, scanning the vast and seemingly empty, expanse of the sky for any sign, for any signal, for any single anomalous blip that would tell us that we are not alone. But we hear nothing. If intelligent life is truly a common and perhaps even an inevitable outcome of the laws of physics and biology, then where is everyone? This is the simple and deeply unsettling question at the heart of the Fermi paradox, a paradox that pits the high statistical probability of extraterrestrial intelligence against the complete and deafening lack of any evidence for it. One of the most sober and most plausible possibilities is that other intelligent civilizations once existed, but are now long and tragically gone. The universe is ancient, more than 13.8 billion years old. This is an almost unimaginable expanse of time, a time scale upon which entire species, entire civilizations, entire biospheres could have evolved, could have flourished, and could have vanished. Millions or even billions of years before human beings ever walked the earth. If alien civilizations rose and fell long before we ever developed the technology to detect them, then we have, in a cosmic sense, simply missed them, their messages, their probes, their great interstellar broadcasts, if they ever sent any, may have passed through our small corner of the galaxy thousands or even millions of years ago, long before we had the means or the inclination to listen, or worse, their signals might still be on their way, a faint and lonely whisper from a long-dead civilization, a message in a bottle that will only arrive at our shores long after our own. Human civilization has itself ceased to exist. This idea that civilizations do not last is a troubling but powerful answer to the Fermi paradox. It suggests that the cosmos may be filled not with thriving interstellar empires, but with the silent and ghostly remnants of once great civilizations, with dead and barren worlds where advanced and perhaps even beautiful beings once lived but are now reduced to a final and eternal silence. There are many, and often terrifying, possible reasons why intelligent and technological civilizations might not endure for very long on a cosmic time scale. One of the most widely and most anxiously discussed of these ideas is the concept of the Great Filter, a hypothetical and seemingly insurmountable barrier that prevents most, if not all, civilizations from ever advancing beyond a certain critical stage. If this filter lies in our past, then it would mean that the emergence of life, or of intelligence, or of technology, is an incredibly and almost miraculously rare event, and that we, as a species, are one of the first and perhaps the only intelligent beings to have ever reached this point in our galaxy. But if the filter lies in our future, then it suggests a far more ominous and far more chilling possibility that all, or nearly all, advanced civilizations, like our own, inevitably, and perhaps even predictably, destroy themselves before they ever reach the level of stable, long-term, interstellar expansion. The ways in which a civilization might self-destruct are numerous, and all too familiar to us. Nuclear war is an obvious and terrifying possibility. A species that develops the incredible and almost godlike power to split the atom gains access to a source of almost limitless energy. But it also, and at the very same time, gains the ability to wipe itself out in a final and fiery instant. If alien civilizations had the same, and often self-destructive, political and social structures as our own, then they may have been just as prone to conflict, to tribalism, to war, and a war fought with weapons far beyond our current, and already terrifying. Technology could have left their entire home planets uninhabitable, extinguishing the bright and precious flame of intelligent life before it ever had the chance to spread beyond its own, fragile and war-torn world, another and perhaps even more insidious. Possibility is environmental collapse, a highly advanced and highly successful. Technological civilization may, like our own, become deeply and perhaps fatally dependent on the finite resources of its home planet, consuming them at an ever-increasing and ultimately unsustainable rate. If they fail to manage their own technological success, if they fail to transition to a more sustainable and more harmonious way of life, they may have depleted their own ecosystems, they may have poisoned their own atmospheres, they may have altered their own climates beyond the point of recovery. Rising temperatures, failing crops, collapsing biospheres, these could have doomed them, leaving their once thriving and once beautiful worlds barren, silent, and dead. If civilizations repeatedly and predictably destroy their own planetary homes before they ever develop the means to leave them, then the galaxy could be filled with a vast and tragic graveyard of dead worlds. Worlds that once hosted the bright and fleeting promise of intelligent life. And then there are the biological threats. A civilization that advances to the point of being able to manipulate its own genetic code to master the arts of genetic engineering and synthetic biology might also, and perhaps inevitably, create diseases that it cannot control. Pandemics, whether natural or artificial, could have swept through their populations, wiping them out in a matter of years. And if intelligent beings experimented with altering their own biological nature, perhaps in the noble pursuit of immortality, or of enhanced intelligence, or of a new and more perfect form of artificial evolution, they may have, with the best of intentions, unintentionally engineered their own and final downfalls. But what if civilizations do not destroy themselves intentionally? Some may have simply been the victims of a cruel and indifferent cosmic chance. They may have fallen victim to the many, and often unpredictable, external threats that the universe can throw at a fragile and planetary biosphere. A massive and civilization-ending asteroid impact, a supervolcanic eruption that plunges their world into a long and deadly volcanic winter, a nearby and powerful gamma-ray burst, the focused and incredibly energetic beam of radiation from a collapsing, massive star that could have sterilized their entire planet in a single, silent flash. Even if a civilization became a spacefaring one, even if they had managed to establish outposts on other planets or moons in their own solar system, they may still have been caught in the path of a truly and unimaginably catastrophic cosmic event. A rogue and wandering black hole, a close and violent collision between two stars, a nearby and powerful supernova explosion, if their entire long-term survival depended on the stability of a single and ultimately fragile planetary, or even a single star system, then the destruction of their home could have meant the final and absolute end of their entire and perhaps billion-year-long species. There is also the even more unsettling and more paranoid possibility that some civilizations were not alone, but that they encountered others who did not have peaceful or even collaborative intentions. If intelligent and technological, species are, by their very nature, competitive and expansionist, then the first civilization to develop the means of interstellar travel might have, as a matter of cold and ruthless logic, viewed any other emerging civilizations as a potential future threat, a threat to be monitored, and perhaps to be eliminated. This is the dark and chilling logic of the dark forest hypothesis, a possible solution to the Fermi paradox that suggests that advanced civilizations remain silent, not because they do not exist, but because they are terrified of attracting the attention of others. If every advanced species assumes that any other species might be hostile, then the safest and most logical course of action is to remain completely and utterly hidden. Those that have, in their naivety, revealed their presence, those that have broadcast their existence to the stars, may have been quickly and silently destroyed. Their bright and hopeful signals a final and tragic beacon that led to their own swift and merciless extinction. If this is true, then the universe might not be empty at all. It might simply be full of a vast and silent population of terrified and hiding civilizations, each one listening and waiting in the dark. And even if some rare and perhaps very lucky civilizations manage to survive all of these immense and often self-inflicted threats, there is still the final and perhaps most profound issue of all, the issue of time itself. The universe operates on a time scale that is so vast, so deep, so almost unimaginably long, that it dwarfs the lifespan of even the most ancient and most stable of civilizations. If an alien civilization flourished 1 billion years ago, and if it lasted for 1 million or even 10 million years before it finally collapsed or disappeared, that would still be an unimaginably long and successful lifespan for a civilization. But in the grand 14 billion year long timeline of the cosmos, it would be nothing more than a fleeting and almost imperceptible moment. If civilizations emerge and then disappear on timescales that are separated by millions or even billions of years, then the likelihood of two independent, intelligent species existing at the same time and also being close enough in space to detect each other is incredibly, vanishingly low. We may have simply arrived too late to the cosmic party, or too early, but perhaps civilizations do not vanish in a final, fiery destruction. Perhaps, instead, they simply retreat. They retreat inward, asufficiently, and perhaps unimaginably. Advanced species may, at some point, simply abandon the messy, difficult, and often dangerous project of physical and interstellar exploration altogether. If their technology reaches the point where they can create perfect and completely immersive virtual worlds, if they can upload their consciousnesses into vast and powerful computational machines, they may have no need and no desire to continue to explore the physical and often disappointing universe. They could have transferred their entire collective existence into a new and more perfect digital space, leaving behind only the silent and empty planets and the dark and rusting cities of their physical and now abandoned past. If this is the case, then the answer to the Fermi paradox is not that civilizations do not last, but that they evolve beyond what we can recognize, beyond what we can detect, beyond what we can even comprehend. The most haunting and most lonely possibility of all, however, is that we are, in fact, the first. That intelligent and technological life is so incredibly and so miraculously rare that we are at this moment the only and the first conscious beings in our entire galaxy, and perhaps even in our entire observable universe, to have reached this particular and perhaps very dangerous stage of development. If this is true, then we are standing at a profound and deeply significant cosmic precipice, facing a choice that may have determined the fate of all those who came before us, if they ever existed at all. We have the potential, the incredible and beautiful potential, to become the first civilization to break free from the Great Filter, to survive our own technological adolescence, to expand beyond our own fragile planet, and to spread the light of life and of consciousness out into the vast and silent stars. But we also face the very same and very real dangers that may have doomed countless and now forgotten others. The silence of the cosmos in this light is not just a scientific mystery. It is a profound and deeply moving warning. If civilizations before us have, in their pride and their folly, destroyed themselves, then we must, with all our collective wisdom and our deepest humility, learn from their silent and tragic mistakes. And if the universe is truly and completely empty, then the great and sacred responsibility falls on us, and on us alone, to ensure that the beautiful and precious experiment of intelligent life does not end here with humanity. We have the ability, the technology, the knowledge to shape our own future, to decide whether we will be just another lost and forgotten civilization, or the first, and perhaps the only, to endure. For now, we continue to search, we continue to listen for the faint and hopeful signals from a distant star. We continue to send our own small and fragile messages out into the vast and silent void. And we continue to hope that we are not too late or too early. Perhaps one day we will hear something, a whisper from a distant star, a faint and beautiful trace of a civilization that survived where others, perhaps, have failed. But until then, we are left with the great and profound silence. And we are left to wonder whether it is the silent and tragic echo of all those who came before us, or the deep and lonely absence of anyone at all. The ultimate fate of our universe is one of the most profound, most beautiful, and most unsettling mysteries in all of cosmology. We exist in a universe that we know had a definite and fiery beginning in the Big Bang. But what happens at the end? Will everything collapse back in on itself in a final cosmic inferno? Will it tear itself apart into a state of absolute and chaotic oblivion? Or will it simply and silently fade away into a cold, dark, and eternal nothingness? No matter which of these grand and often terrifying scenarios plays out, there will be a final and absolute horizon, a point in the far to distant future where no observer, no matter how advanced, no matter how patient, will ever be able to witness what comes next. The very end of the universe will not just be lost to us, it will be lost to all of existence itself. To understand the future, we must first look to the past and to the present. The universe, as we have seen, began with the Big Bang, a moment of almost unimaginable energy and expansion that marked the creation of space and time itself. And from that initial, singular moment, everything has been expanding outwards, forming the vast and beautiful tapestry of galaxies, of stars, of planets that we see today. But the force that first set the universe in motion, the force of expansion, has never stopped. For the first few billion years of cosmic history, the force of gravity, the mutual attractive pull of all the matter in the universe, acted as a powerful cosmic brake, slowing down the rate of this expansion. But then, about 5 billion years ago, something changed. A new and mysterious force, an invisible and repulsive energy that we call dark energy, began to win the cosmic tug of war. And today, we know that dark energy is not just winning, It is dominant. The universe is not just expanding, its expansion is accelerating, growing faster and faster with each passing moment. And as time goes on, the distant galaxies will continue to drift farther and farther apart. What we see in our night sky today, the beautiful and seemingly eternal spiral and elliptical galaxies, will look drastically different in the far distant future. Eventually, one by one, these entire and magnificent island universes will disappear from our view, slipping silently and irrevocably beyond our cosmic event horizon, their light forever unable to reach us again. This alone is a strange and deeply terrifying thought. One by one, the universe is erasing itself from our own local perspective. But the true and ultimate fate of our universe depends entirely on the nature and the future behavior of this strange and mysterious dark energy. And scientists have theorized several possible and often haunting endings to our cosmic story. One of the most dramatic and most violent of these possible endings is the Big Rip. If dark energy is not a constant, but is a form of phantom energy that grows stronger and more repulsive over time, then it will not just continue to push the distant galaxies apart, it will eventually begin to tear apart the very fabric of reality itself. First, the great clusters of galaxies, the largest gravitationally bound structures in the universe, will be dissolved, their constituent galaxies flung out into the expanding void. Then, as the repulsive force of the phantom energy continues to grow, it will overcome the gravity of the individual galaxies themselves, breaking them apart, and leaving their billions of stars stranded and alone in the darkness. As the end approaches, the force will become so strong that it will overcome the gravity that holds our own solar system together, tearing the planets from their orbits and leaving them to wander, dark and cold, through an increasingly and violently unstable reality. Eventually, in the final, fleeting moments of the cosmos, the force of the Big Rip will overcome the electromagnetic forces that hold the atoms themselves together. And then, finally, the strong nuclear force that binds the protons and the neutrons in the atomic nucleus. Everything, matter, space, and perhaps even time itself will be ripped apart at the most fundamental subatomic level. The universe will not just end, it will be violently and completely destroyed. Its every structure, at every scale, reduced to a shower of free and causally disconnected fundamental particles. But there is another, and perhaps even quieter and more haunting fate that may await us, the heat death, also known as the Big Freeze. In this scenario, the cosmic expansion, driven by a constant dark energy, continues, but at a steady and ever-accelerating rate. The universe will continue to spread all of its matter and energy out over an ever larger volume of space until nothing can ever interact with anything else again. The stars will slowly and one by one exhaust their nuclear fuel, their bright and beautiful flames flickering and dying out, leaving behind only the cold, dark, and silent remnants of white dwarfs, neutron stars, and black holes. The galaxies themselves will fade into an eternal darkness, and then, over immense and almost unimaginable timescales, even these last remaining structures will begin to decay. The protons themselves may, according to some theories, be unstable and will, over trillions upon trillions of years, slowly decay into a sea of lighter particles and radiation. And the black holes, the last and most massive structures in the universe, will slowly and silently evaporate, radiating away their mass energy through the subtle quantum process of Hawking radiation. In the end, after an almost infinite amount of time has passed, The universe will be a cold, dark, empty, and lifeless place. There will be no new stars being born. There will be no galaxies colliding. There will be no motion, no warmth, no change. The universe will not have exploded. It will not have collapsed. It will have simply and quietly stopped doing anything at all. This is, for many, the most haunting and most existentially terrifying of all possible endings. Not a fiery and dramatic cataclysm, but a slow, cold, and inevitable fading into an absolute and eternal nothingness. And the worst and most poignant part of this story is that no one will be left to witness it. If any far future civilizations manage to survive for these billions or even trillions of years, they will slowly and inexorably fade with the dying stars. The last conscious being in the entire universe will have no one to tell their story to, no one to hear their final and lonely words. When the very last usable source of energy in the cosmos is finally used up, existence itself, in all its beauty and its complexity, will go silent. But there is still one more possibility, one that offers the tiniest and perhaps most beautiful glimmer of hope. Some theories, as we have seen, suggest that the universe may be cyclical, that after it fades or after it rips apart, a new universe could be born from its ashes. If this is true, then the end is not truly the end, but is just the beginning of something new, a new chapter in an eternal cosmic story. However, even in this hopeful and beautiful picture, our own universe, our own story, would still be lost. If a new universe is born, it will be completely and utterly disconnected from our own. There will be no way to remember what came before, no trace of the past that can be left behind. Our universe, with all its beauty, all its complexity, all its life, everything that we know, everything that we have ever been, will still be lost forever to the sands of an eternal and unforgiving time. No matter what happens, no matter which of these grand cosmic scenarios plays out, the final and ultimate horizon of our universe is a line that no one and no thing will ever be able to cross. The end will come, and there will be nothing left to see it. It is a thought that is both profoundly humbling and deeply and beautifully sad. The universe is a grand and glorious and ultimately tragic story, and we are living in its middle, and perhaps its most beautiful and most interesting chapter. And the very fact that we are here now to witness it, to understand it, to appreciate its fleeting and beautiful and often terrifying glory is a miracle that is almost too profound for words. The universe, in all its vast and often mysterious splendor, is an endless expanse of wonder, a cosmic ocean filled with secrets that stretch far beyond the limits of our current, and perhaps even our future, understanding. It is a reality that calls to us, that ignites our curiosity, that fuels our ambition, and that urges us to explore the great and often terrifying unknown. And yet, for all our dreams of reaching the stars, for all our technological ingenuity, for all our boundless human perseverance, there are places in this vast and beautiful cosmos that we will never be able to set foot in, realms that are so distant, so hidden, or so fundamentally and physically unreachable that they will remain forever beyond our grasp. These are the forbidden zones of the universe, and no amount of technology, no future, scientific breakthrough, no amount of pure human will ever allow us to breach their silent and eternal boundaries. Some of these forbidden and often tragic places are being actively and constantly created right now as we speak, torn from our view by the relentless and ever-accelerating expansion of space itself, with each passing moment entire and magnificent galaxies, each containing billions of stars and perhaps billions of planets, are racing away from us at speeds that are faster than the speed of light, carried along on the ever-growing and ever-stretching fabric of the cosmos. The deeper we look into space, the more we realize just how much of the universe is already, and forever, gone. Regions of the cosmos that were once in the distant and ancient past, within our causal reach, now exist beyond a point, beyond a horizon, that we can never, ever cross. Even if we could somehow, one day, develop the technology for engines that could propel us at the very speed of light itself, it would not be enough. The very space between us and these distant, and now forbidden, realms is expanding too fast for us to ever be able to catch up. And even much closer to home, in our own local cosmic neighborhood, the ultimate barriers of the universe are just as real and just as insurmountable. Black holes, the most enigmatic and most powerful objects in all of existence, hold deep and perhaps eternal secrets that we may never be able to uncover. Their event horizons are not just a physical boundary, they are a one-way and absolute door to oblivion. Anything that crosses this point of no return, no matter how advanced, no matter how powerful, no matter how resilient, will never be able to come back, not even light, the fastest thing in the universe, can escape their immense and unforgiving gravitational pull. And whatever information, whatever story, whatever reality falls inside is, for all practical purposes, effectively and completely erased from the universe as we know it. The very nature of space and of time within a black hole is a deep and profound mystery to us, and it is a mystery that may be, in its very essence, forever unknowable. If we could somehow send a probe, a robotic emissary, into one of these dark and silent abysses, its signals, its data, its final desperate messages would never be able to reach us. And if an astronaut, a brave and perhaps foolish explorer, were to venture too close, they would be stretched and crushed and torn apart into a stream of fundamental particles, their body, their mind, their story, all reduced to a final and silent nothingness, long before they could ever hope to tell us what they had found. The heart of a black hole is not just a forbidden zone, it is the ultimate and most absolute point of no return. And what about the true and ultimate beginning of everything? The very first fleeting moments after the Big Bang hold the answers to some of the deepest and most profound questions that humanity has ever asked, questions that could explain our entire and often mysterious existence, and yet they are locked away from us forever, behind a thick and impenetrable veil of physics that we cannot and may never be able to penetrate. The universe, in its extreme and fiery infancy, was so incredibly hot and so unimaginably dense that light itself, the very photons that carry information across the cosmos, was unable to travel freely. The early universe was an opaque and chaotic fog, and this means that no telescope, no matter how powerful, no matter how sophisticated, will ever be able to directly see what truly happened at the very start. The first and most crucial moments of time itself exist behind an eternal and insurmountable wall. a forbidden zone that is not in space, but in time. But perhaps the most unsettling and most humbling reality of all is not just that there are places and times that we can never reach, but that the number of these forbidden zones is constantly and inexorably growing every single second. New and previously accessible regions of space are drifting silently and forever beyond our ability to ever explore. The universe is expanding, and with it, the possibilities for our own, human and cosmic, exploration are, in a very real and very tragic sense, shrinking. 1 trillion years from now, there will come a time when our own familiar Milky Way galaxy is the only thing that is visible in the vast and dark night sky. Every other galaxy, every other island universe will have vanished forever, beyond our cosmic horizon, never to be seen again. Future civilizations, no matter how advanced, no matter how curious, will never even know of the vast and beautiful cosmos that we, in our own brief and precious moment of cosmic history, are still able to glimpse. To them, the universe will appear as a lonely and isolated island, a single, solitary galaxy in an infinite and seemingly empty void. And yet, despite knowing all of this, despite knowing that there are limits, that there are boundaries, that there are places we can never go, we continue to reach, we continue to wonder, we continue to dream, even if we can never set foot in these lost and forbidden places. Even if the universe has set certain and absolute limits that we can never, ever cross, our desire, our insatiable and beautiful human desire to understand is limitless. And perhaps, in the end, that is what truly and most profoundly defines us. Not where we can go, but what we seek to know. The forbidden zones of the universe, the lost galaxies, the dark hearts of black holes, the silent and ancient beginning of time, may never be explored in person, but they will always and forever be explored in our minds, in our theories, in our stories, in our dreams, and in that sense, in the beautiful and often tragic and endlessly creative journey of the human imagination. The quest, the exploration, the adventure never, ever truly ends. Have you ever stopped to wonder what consciousness really is, or why the smallest particles in our universe, like electrons and photons, behave so strangely, defying the rules of everyday life? For centuries, these two mysteries, the nature of the mind and the nature of matter, have been pursued along separate, parallel tracks. But what if these tracks are not parallel at all? What if they are destined to converge? A bold and speculative idea, known as the theory of quantum consciousness, suggests that these two great mysteries might be two sides of the same deep coin. It proposes that our minds, the very seat of our subjective experience, could operate on the same mind-bending principles that govern the bizarre and beautiful world of the quantum realm. In quantum mechanics, as we have seen, particles can exist in a superposition of multiple states at once, a ghostly blend of possibilities. They can be instantaneously connected across vast cosmic distances through the spooky phenomenon of entanglement, and their very reality seems to be shaped by the act of observation. Could our minds work in a similar way? Could our thoughts and ideas exist as a superposition of unformed potentials, only crystallizing into a definite concept when we focus our attention? Could our feelings of connection, of empathy, of intuition be a macroscopic echo of quantum entanglement? And could consciousness itself be the ultimate observer, the mysterious agent that collapses the wave function of possibility into the definite, classical reality we experience. This is a breathtaking idea, one that challenges our most fundamental assumptions about both the physical world and our own inner selves. It is a journey to the very edge of science, a place where physics, neuroscience, and philosophy meet. A place where the mysteries of the cosmos and the mysteries of the mind might just be one and the same. In our everyday classical world, the act of observation is a passive one. When we look at a cup of coffee on a table, we assume that our gaze does not affect the cup's properties. The cup is there. It has a definite position, a definite temperature, whether we are looking at it or not. But in the quantum world, the rules are different. Here, the simple, seemingly innocent act of observing a particle can fundamentally change its behavior. This is the observer effect, one of the most puzzling and profound phenomena in all of science. But what precisely does it mean? It is not simply that our measuring devices are clumsy and inevitably disturb the delicate quantum systems they are trying to measure, though that is certainly part of the story. To see an electron, for example, we have to bounce a photon of light off of it. This photon carries energy and momentum, and in the act of a collision, it will inevitably give the electron a kick, changing its state. It is like trying to determine the precise position of a billiard ball by hitting it with another billiard ball. The very act of measurement changes the thing you are trying to measure. But the observer effect in quantum mechanics is deeper and stranger than this. It is not just about a physical disturbance. It is about the role of information and the nature of reality itself. It is intimately tied to the concept of the collapse of the wave function. In the quantum world, before a measurement is made, a particle is described by a wave function, a mathematical object that represents a superposition of all its possible states. An electron does not have a single position. It is a cloud of probability. The moment we make a measurement, the moment we gain information about its position, this wave function is said to collapse. The cloud of possibility vanishes, and the electron is found at a single, definite location. Why does this happen? Why does the act of observation force the universe to abandon its ghostly, probabilistic nature and choose a single, classical reality? This is the heart of the quantum measurement problem, and it is a mystery that has no universally accepted answer. One of the oldest and most influential attempts to address it is the Copenhagen interpretation, developed by the founding fathers of quantum mechanics, Niels Bohr and Werner Heisenberg. In this view, there is a fundamental distinction between the quantum world of microscopic systems and the classical world of our macroscopic measuring devices. Quantum systems do not have definite properties until they are measured. The act of measurement is what brings these properties into being. An electron does not have a position until we measure it. This is a pragmatic and somewhat instrumentalist view. It provides a set of rules that work incredibly well for making predictions, but it does not offer a deep, ontological explanation for why the rules are the way they are. It leaves the process of measurement as a kind of black box, a mysterious and unexplained, shifty split between the quantum and the classical. The philosophical unease created by the Copenhagen interpretation, with its seemingly arbitrary division of the world and its central, unexplained role for the observer, has led to a host of alternative interpretations, each offering a different, and often equally bizarre, picture of reality. The most famous of these is the many worlds interpretation, first proposed by the physicist Hugh Everett III in a bold and elegant move. Everett suggested that the collapse of the wave function never happens. The wave function and its smooth, continuous evolution according to the Schrödinger equation is the whole story. When a measurement is made, the universe does not choose one outcome. Instead, all possible outcomes are realized, each in its own, separate, parallel universe. The universe itself splits or branches into a multitude of realities. In one universe, the electron is found at position A. In another, it is found at position B. The observer also splits, with one version of you experiencing outcome A and another version experiencing outcome B. In this view, Schrödinger's cat is never in a superposition of alive and dead. There are simply two separate universes, one in which the cat is alive, and one in which it is dead. This is a breathtakingly grand and economical vision. It does away with the mysterious collapse and the special status of the observer, and it restores a kind of deterministic, universal reality. But it does so at the price of postulating an unobservable and possibly infinite number of parallel worlds. At the other end of the interpretational spectrum lies a class of theories that seek to restore a more classical, intuitive picture of reality. The pilot wave theory, first conceived by Louis de Broglie and later rediscovered and developed by David Bohm, proposes that quantum particles are, in fact, classical-like particles. They always have a definite position, even when we are not looking. The wave function is not just a description of probabilities. It is a real, physical pilot wave that guides the motion of the particle. The particle is like a surfer riding on the surface of this underlying, invisible wave. In this picture, the apparent randomness of quantum mechanics is not fundamental, but is a result of our ignorance of the particle's precise initial position and the complex non-local nature of the pilot wave. This is a fully deterministic theory that reproduces all the statistical predictions of standard quantum mechanics. But it does so by introducing a new, unobservable entity, the pilot wave, and by embracing a deep and spooky non-locality, where the motion of a particle here can be instantaneously influenced by the state of the entire universe. And then there are the objective collapse theories, which propose that the collapse of the wave function is a real physical process that happens spontaneously, without the need for an observer. The collapse is a random, probabilistic event, and its likelihood depends on the size and complexity of the system. For a single, isolated particle, the chance of a spontaneous collapse is infinitesimally small, so it can maintain its superpositional nature for a long time. But for a macroscopic object like a cat, which is made of trillions of entangled particles, the probability of a collapse occurring in one of its constituent particles becomes overwhelmingly high, triggering a rapid chain reaction collapse of the entire system. This elegantly explains why we never see macroscopic superpositions, but it does so by modifying the fundamental Schrödinger equation and introducing new, and as yet unobserved, physical parameters. The ongoing debate between these different interpretations highlights the profound and still unresolved conceptual crisis at the heart of modern physics. We have a mathematical formalism that works with stunning, unprecedented accuracy, but we have no consensus on what it is telling us about the nature of reality. Is the universe fundamentally probabilistic or deterministic? Is reality created by observation, or does it exist independently of us? Is there one world, or are there many? And what, if any, is the role of consciousness in this cosmic drama? These are questions that may not have a final scientific answer, but they are questions that force us to confront the limits of our own understanding and to stand in a state of profound and humble awe before the deep, beautiful, and endlessly fascinating mystery of the quantum world. The principle of superposition, the idea that a quantum particle can exist in a multiplicity of states at once, is not just a strange feature of the subatomic world. It is a powerful lens through which we can view the nature of our own consciousness. While the idea of a quantum mind is highly speculative and on the very fringes of mainstream science, the metaphorical resonance between the quantum world and our own, Inner experience is undeniably profound and thought-provoking. Consider the nature of a thought. Before a thought becomes a clear, definite, and articulated concept, it often exists as a vague, fuzzy, and unformed potential. It is a superposition of different possible meanings, different emotional colorings, different associative connections. It is only through the act of focusing our attention, of measuring our own mental state, that this superposition collapses into a single, definite thought. The creative process is a particularly clear example of this. An artist, a writer, a musician, often speaks of being in a state of flow, a state where they are open to a vast field of possibilities, a state where ideas seem to emerge spontaneously, without conscious effort. This is a state of mental superposition, a state where the mind is not locked into a single, linear track of thought, but is free to explore the vast, interconnected web of the unconscious. The aha moment, the flash of insight that solves a difficult problem, is the experience of a new and previously unconsidered possibility collapsing into a definite reality. It is a moment of creative quantum leap. The experience of making a decision is another powerful parallel. Before we make a significant choice, we often feel torn between different options. We can see the merits of each path. We can imagine the different futures that each choice would lead to. We are, in a very real sense, in a superposition of all these potential futures. The act of making the decision, of committing to one path, is the act of collapsing this superposition. It is a creative, world-shaping act that transforms the potential into the actual. This is why decisions can be so difficult and so anxiety-provoking. It is the existential weight of collapsing a whole universe of possibilities into a single, irreversible reality. But the most universal and profound experience of mental superposition is the one we all enter every night, the state of sleep and dreaming. As we drift off to sleep, the collapsed, classical self of our waking life begins to decohere. The rigid boundaries of the ego dissolve, and we are immersed in the fluid, multi-layered, and superpositional world of the unconscious. In our dreams, we are not a single, coherent identity. We can be a child and an old person at the same time. We can be both the pursuer and the pursued. We can feel both terror and exhilaration simultaneously. The normal rules of logic, of time, of identity are suspended. The dream is the psyche's nightly return to its own native quantum state, a state of pure, uncollapsed potential. This is not to say that the brain is a literal quantum computer, or that our thoughts are actual quantum states. The brain is a warm, wet, and noisy biological system, an environment that is generally thought to be far too disruptive for the delicate, coherent states of the quantum world to survive for any significant amount of time. The challenges of decoherence are immense, and yet the metaphorical parallel is too strong to ignore. The language of quantum mechanics of superposition, of potential, of collapse, of interconnectedness provides us with a new and remarkably rich vocabulary for describing the deep and often paradoxical nature of our own subjective experience. It invites us to see our minds not as simple, classical machines, but as complex, dynamic, and endlessly creative quantum-like systems. It suggests that the strangeness of the quantum world is not something that is out there in the abstract realm of particles and fields. It is something that is in here, in the very fabric of our own conscious awareness. And by exploring the mysteries of the quantum world, we may, in the end, be exploring the deepest and most profound mysteries of ourselves. The phenomenon of quantum entanglement, the spooky action at a distance that so perplexed Einstein, is a direct and powerful testament to the non-local and holistic nature of the universe. It tells us that our classical intuition of a world made up of separate, independent objects is a profound illusion. At a fundamental level, the universe is not a collection of things, It is a network of relationships, a single, indivisible whole. When two particles become entangled, they are no longer two separate entities. They are two aspects of a single, unified quantum state, described by a single wave function. The measurement of one particle is not an action on a separate object. It is a measurement of the entire entangled system, an act that instantaneously collapses the wave function of the whole, no matter how far apart its constituent parts may be. This is a concept that is so counterintuitive that it has taken decades of increasingly sophisticated experiments, like the Bell tests, to convince the scientific community of its reality. But the evidence is now overwhelming. The universe is, in some deep and mysterious way, non-local. This has profound implications that ripple out from the world of physics into the realms of philosophy, spirituality, and our own personal experience. If the universe is fundamentally interconnected, then the sense of separation we feel as individual beings is not the ultimate truth. We are not isolated, skin-encapsulated egos, adrift in a cold, indifferent cosmos. We are, in a very real physical sense, entangled with each other, with the planet, and with the entire history of the universe. The atoms in our bodies are the recycled stardust of ancient, long-dead stars. The information in our DNA is a 4-billion-year-old story that connects us to the very first life on Earth. We are not just in the universe, we are the universe, experiencing itself. This sense of interconnectedness is not just an abstract philosophical idea. It is an experience that we can all have, an experience that is often most accessible in states of consciousness where the dominance of the ego is relaxed, in moments of deep love, of profound empathy, of awe in the face of natural beauty. Our sense of a separate self can dissolve, and we can feel a deep and powerful sense of unity with the person, the place, or the moment we are experiencing. These are moments of conscious entanglement, moments when we touch the underlying, holistic reality of our own being. Sleep, and particularly the dream state, is a nightly immersion in this entangled reality. As the boundaries of the self become porous, our consciousness is free to roam the vast, non-local network of the unconscious. In our dreams, we can connect with people and places that are distant in space and time. We can have vivid, emotionally resonant encounters with loved ones who are far away, or even with those who have passed on. We can experience a deep sense of participation mystique, a feeling of merging with the archetypal energies of the collective unconscious. These are not just random neurological firings. They are the psyche's way of exploring its own vast, entangled web of relationships. They are a reminder that our connections to others are not severed by physical distance or even by death. The information, the emotional resonance, the shared history, persists in the non-local field of our own, and the collective consciousness. The practical applications of entanglement in the realms of quantum computing, quantum cryptographies, and quantum teleportation are already beginning to transform our technological landscape. A quantum internet, based on the transmission of entangled states, could one day provide a form of communication that is fundamentally secure, as any attempt to eavesdrop on the communication would instantly break the entanglement and be detected. Quantum teleportation, while not the beam-me-up biscotti of science fiction, allows for the perfect transmission of the quantum state of a particle from one location to another, a technology that could be the backbone of future quantum networks. But the true revolution of entanglement may be a philosophical one. It is a concept that is forcing us to abandon our old mechanistic and fragmented worldview and to embrace a new, holistic, and interconnected vision of reality. It is the scientific confirmation of the ancient spiritual insight that we are all one. And every night, as we surrender to the mystery of sleep, we are given the chance to experience this profound truth directly, to remember our deep and beautiful entanglement with the entire cosmic web of existence. The quantum vacuum, the so-called empty space that fills the universe, is not a void of nothingness, but a plenum of potential, a seething, energetic sea from which the entire manifest world arises. This is the realm of virtual particles, a concept that is as central to modern physics as it is challenging to our classical intuition. Virtual particles are not real particles in the sense that we can put them in a detector and measure their properties. They are fleeting, transient fluctuations of the quantum fields, phantom entities that borrow a tiny amount of energy from the vacuum to pop into existence for an immeasurably short time, only to annihilate each other and disappear back into the void. Their existence is a direct consequence of the energy-time uncertainty principle. For a very brief moment, the law of conservation of energy can be violated, as long as the energy debt is quickly repaid. The quantum vacuum is a cosmic loan shark, constantly lending out and recalling these tiny packets of existence. But these are not just a mathematical fiction, a computational convenience used by physicists to make their equations work. Virtual particles have real, measurable, and profound effects on the world. We have already seen how they are responsible for the Casimir effect, the strange, attractive force between two plates in a vacuum. They are also responsible for some of the most precise and well-tested predictions of quantum electrodynamics, the quantum theory of light and matter. The magnetic moment of an electron, for example, is not a simple, fixed value. It is slightly, but measurably, different from the value predicted by the simplest form of the theory. This tiny discrepancy, known as the anomalous magnetic moment, is perfectly explained by accounting for the electron's interaction with the cloud of virtual photons and electron-positron pairs that are constantly bubbling around it. The agreement between the theoretical calculation and the experimental measurement of this value is one of the most stunning triumphs in the history of science, a testament to the very real existence of this seemingly ghostly virtual world. The concept of virtual particles also provides a new and powerful way to understand the nature of the fundamental forces. In quantum field theory, all forces are mediated by the exchange of virtual particles. The electromagnetic force between two charged particles is the result of them exchanging virtual photons. The strong nuclear force that binds quarks together inside protons and neutrons is mediated by the exchange of virtual gluons. The weak nuclear force, responsible for radioactive decay, is carried by virtual W and Z bosons. The seemingly solid and continuous forces of our macroscopic world are, at a fundamental level, a grainy, pixelated, and probabilistic exchange of these transient quantum messengers. This has profound implications for our understanding of reality. It suggests that the distinction between matter and force, between substance and interaction, is not as clear as we once thought. They are both different manifestations of the same underlying quantum fields, but the role of virtual particles extends even to the grandest cosmological scales. The phenomenon of Hawking radiation, the faint, thermal glow that is predicted to be emitted by black holes, is a direct consequence of virtual particle creation at the event horizon. A virtual particle-antiparticle pair can be created right at the edge of the black hole, if one particle falls in and the other escapes. The escaping particle can no longer annihilate with its partner. It becomes a real particle, carrying away a tiny amount of the black hole's mass energy. This process, over immense timescales, causes the black hole to slowly evaporate. It is a beautiful and profound example of how the subtle, quantum fluctuations of the vacuum can have a dramatic and tangible effect on the most massive and powerful objects in the cosmos. The world of virtual particles is a world that is forever hidden from our direct view, a world that exists on the very edge of being and non-being. But it is a world whose influence is everywhere, from the precise properties of a single electron to the ultimate fate of a giant black hole. It is the invisible, energetic, and endlessly creative engine that drives the quantum universe. The ability of a quantum particle to tunnel through a barrier that it classically should not have the energy to overcome is one of the most striking and non-intuitive predictions of quantum mechanics. It is a phenomenon that relies on the wave-like nature of particles and the probabilistic heart of the quantum world. A particle's wave function does not stop abruptly at a barrier. It decays exponentially into it. If the barrier is thin enough, there is a small but non-zeroed probability that the wave function will still have some amplitude on the other side, meaning there is a finite chance of finding the particle there. This is not just a theoretical curiosity. It is a process that is essential to life, the universe, and everything. The sun shines because of quantum tunneling. The core of the sun is a furnace of nuclear fusion, where hydrogen nuclei are fused together to form helium, releasing a tremendous amount of energy. But the temperature and pressure in the sun's core, while immense, are not quite high enough for these positively charged nuclei to overcome their mutual electrostatic repulsion and get close enough to fuse in a classical way. It is only because of the magic of quantum tunneling that they can bypass this energy barrier and initiate the fusion reactions that power our star and make life on Earth possible. Without quantum tunneling, the stars would not shine, and the universe would be a cold, dark, and lifeless place. Quantum tunneling is also the principle behind the technology of the scanning tunneling microscope, a device that has allowed us to see individual atoms for the first time. The STM works by bringing a razor-sharp metal tip incredibly close to a conducting surface. A tiny voltage is applied, and because of quantum tunneling, a small current of electrons can tunnel across the vacuum gap between the tip and the surface. This tunneling current is exquisitely sensitive to the distance between the tip and the surface, by scanning the tip across the surface and keeping the tunneling current constant. A computer can build up a three-dimensional atomic resolution map of the surface. This technology has revolutionized the fields of materials, science, chemistry, and biology, allowing us to see and manipulate matter at its most fundamental level. But the implications of quantum tunneling extend even further, into the realm of our own modern digital technology. The flash memory that is used in our computers, smartphones, and USB drives works by storing electrons in a floating gate, a tiny island of conducting material that is surrounded by a thin insulating barrier. To write information, a voltage is applied that allows electrons to tunnel through this barrier and become trapped in the floating gate. To erase the information, the voltage is reversed, and the electrons tunnel back out. Every time you save a file or take a picture with your phone, you are relying on the strange, probabilistic, and deeply non-classical phenomenon of quantum tunneling. But perhaps the most profound and speculative application of quantum tunneling is in the origin of the universe itself. As we have seen, some cosmological models propose that our entire universe may have been born from a quantum tunneling event, a spontaneous transition from a state of nothing to a state of something. This is the ultimate act of tunneling, a leap not through a physical barrier, but through the metaphysical barrier between non-existence and existence. Quantum tunneling is a beautiful and powerful reminder that the universe is not a deterministic machine, but a world of probability and potential. It tells us that barriers are not always absolute, that the impossible can sometimes happen, and that even in the face of insurmountable odds, there is always a chance, however small, of a breakthrough. It is a principle of hope, of transformation, of creative surprise, a principle that is written into the very fabric of our quantum reality. The Heisenberg uncertainty principle is not just a statement about the limits of our measurement capabilities. It is a deep and fundamental principle that reveals the inherent, irreducible fuzziness of the quantum world. It is the universe's way of ensuring that reality is never static, never fixed, and never completely knowable. The trade-off between position and momentum is the classic example. But the principle applies to other pairs of conjugate variables as well, such as energy and time. The more precisely you know the energy of a quantum system, the less precisely you can know the duration over which that energy is defined, and vice versa. This energy-time uncertainty is the principle that allows for the existence of virtual particles, the fleeting fluctuations of the quantum vacuum. It is the source of the universe's zero-point energy, the irreducible quantum jiggle that prevents anything from ever being truly at rest. It is a principle that replaces the classical world of certainty with a world of probability, a world where the future is not predetermined, but is a landscape of open potential. This has profound philosophical implications. It suggests that the universe, at its core, is not a clockwork machine, but a creative, spontaneous, and endlessly unfolding process. The inherent uncertainty of the quantum world is not a flaw. It is the very source of its novelty, its capacity for the emergence of new and unexpected forms. This resonates deeply with our own subjective experience of being. We are not deterministic automatons, our lives unfolding along a pre-written script. We are beings of choice, of creativity, of potential. We live in a constant state of uncertainty, and it is this very uncertainty that gives our lives meaning, that makes our choices matter. If the future were completely determined, there would be no freedom, no responsibility, no art, no love. The uncertainty principle is the physical guarantee of our own human freedom. It is the universe's way of saying, I have not yet decided. And this sense of openness, of potential, is an experience that is most accessible to us in the quiet, liminal state of our own minds, as we relax our focused, goal-oriented, and certainty-seeking waking consciousness, as we drift into the gentle, associative flow of daydreams or the deep, symbolic world of our sleep. We are entering a realm that is governed by a logic that is more akin to the quantum world. It is a realm where the rigid boundaries between self and other, between past and future, between reality and imagination, become fluid and permeable. It is a realm where new connections can be made, where old patterns can be broken, where new insights can spontaneously emerge. This is the creative power of the unconscious, the mind's own innate capacity for navigating the landscape of uncertainty. The uncertainty principle is not a statement of our ignorance. It is a statement about the nature of reality. It is a celebration of the possible, a testament to the fact that the universe is not a closed, finished system, but an open, creative, and endlessly surprising adventure. And we, as conscious, questioning, and dreaming beings, are privileged to be a part of that adventure. The Copenhagen interpretation, for all its pragmatic success, leaves a deep sense of philosophical unease. Its insistence on a fundamental and unexplained, split between the quantum and classical worlds, and its elevation of the act of measurement to a special collapse-inducing status, seems to many physicists to be an incomplete and unsatisfying picture of reality. This has led to a century-long search for alternative interpretations, each attempting to provide a more coherent and ontologically complete story of the quantum world. The many worlds interpretation, with its breathtaking vision of a constantly branching multiverse, offers a radically different perspective. It eliminates the mystery of the collapse by simply denying that it ever happens. The wave function is the whole story, and its smooth, deterministic evolution is the only law. This is a picture of immense elegance and simplicity, but it comes at the cost of a bloated and unobservable ontology. We are asked to believe in the existence of an infinite number of parallel universes, universes that are, by their very nature, completely inaccessible to us. Is this a price worth paying for theoretical consistency? The pilot wave theory of de Broglie and Bohm offers another path. It restores a kind of classical realism and determinism to the quantum world. But it does so by introducing a new, unobservable entity, the pilot wave, and by embracing a deep and spooky non-locality that seems to be in tension with the spirit, if not the letter, of Einstein's relativity. It is a vision of a hidden clockwork universe, a universe where the apparent randomness is just an illusion of our own ignorance. And then there are the objective collapse theories, which seek to make the collapse a real physical and universal process, independent of any observer. These theories modify the fundamental Schrödinger equation, adding new, nonlinear, and stochastic terms that cause the wave function to spontaneously collapse. This is a scientifically respectable approach, as it makes new, testable predictions. A spontaneous collapse process should, for example, produce a tiny, but constant, amount of heat, a spontaneous heating of the universe that could, in principle, be detected. So far, no such effect has been found, which places tight constraints on these models. But the search continues. The ongoing debate between these different interpretations is not just a technical squabble among physicists. It is a debate about the very nature of reality, about the relationship between the mind and the world, between the potential and the actual, between the one and the many. It is a debate that touches on some of the deepest and most enduring questions of philosophy. And it is a debate that is unlikely to be settled by a single killer experiment. It is more likely that our understanding will evolve through a slow, cumulative process of theoretical refinement and experimental constraint. A process that may lead us not to a single, final correct interpretation, but to a new, and perhaps more profound, synthesis that transcends our current, limited categories of thought. The strangeness of the quantum world is not a problem to be solved. It is a reality to be understood. And in grappling with its mysteries, we are not just doing physics. We are engaged in a deep and deeply human act of philosophical inquiry, a quest to understand our own strange and beautiful place in a universe that is far more mysterious, more interconnected, and more full of possibility than our classical intuition could ever have imagined. The quantum world is not just a realm of strange and counterintuitive phenomena, it is also the engine of our modern technological world. The principles of quantum mechanics. Once the esoteric domain of a handful of theoretical physicists, are now at the heart of some of our most advanced and transformative technologies. Quantum computing is perhaps the most famous and most ambitious of these. By harnessing the principles of superposition and entanglement, quantum computers have the potential to solve certain classes of problems, like factoring large numbers, simulating complex quantum systems, and searching vast databases at speeds that are exponentially faster than any classical computer. This could revolutionize fields as diverse as medicine, materials science, finance, and artificial intelligence. A quantum computer could simulate the behavior of a new drug molecule with perfect accuracy, allowing for the design of more effective and personalized medicines. It could discover new materials with exotic properties, like room temperature superconductors. It could break the encryption codes that currently protect our global financial and communication systems, a prospect that is driving the parallel development of quantum-safe cryptography. But building a large-scale, fault-tolerant quantum computer is an immense scientific and engineering challenge. The quantum states of the qubits are incredibly fragile and are easily disturbed by their environment, a process known as decoherence. Protecting these delicate quantum states from the noise of the outside world is the central challenge in the field. And it is a challenge that requires a deep and practical understanding of the very quantum phenomena we have been discussing. Quantum cryptography offers a more near-term and equally revolutionary application of quantum principles. By using the properties of single photons or entangled particle pairs to encode and transmit information, it is possible to create a communication channel that is fundamentally secure. The laws of quantum mechanics themselves guarantee its security. The uncertainty principle dictates that any attempt by an eavesdropper to measure the quantum state of the photons will inevitably disturb them, and this disturbance can be detected by the legitimate users. Entanglement-based systems offer an even more robust security, as the non-local correlations between the entangled particles can be used to verify the integrity of the communication channel. These quantum communication networks are already being built and tested, and they will likely form the backbone of a future, ultra-secure quantum internet. Quantum sensors are another area where quantum mechanics is having a profound impact. By exploiting the exquisite sensitivity of quantum systems to their environment, it is possible to build sensors of unprecedented precision. Atomic clocks, which use the regular quantum oscillations of atoms as their timekeeping element, are the most accurate timekeepers ever built. They are the heart of our global positioning system, and they are being used to test the predictions of general relativity with incredible accuracy. Quantum magnetometers, based on the spin of nitrogen vacancy centers in diamond, can detect magnetic fields that are 1 billion times weaker than the Earth's magnetic field, with applications in medical imaging and materials science. And gravitational wave detectors like LIGO use quantum optics and squeezed light to measure the tiny subatomic scale ripples in space-time caused by the collision of distant black holes. Even the realm of biology is not immune to the quantum revolution. The emerging field of quantum biology is exploring the possibility that some fundamental life processes, like photosynthesis, avian navigation, and the sense of smell, may rely on quantum effects to function. The high efficiency of energy transfer in photosynthesis, for example, may be due to a process of quantum coherence, where the energy explores multiple pathways simultaneously to find the most efficient route. These are still controversial and developing ideas, but they hint at a deep and beautiful connection between the fundamental laws of physics and the emergent complexity of life itself. The quantum revolution is not just a revolution in our understanding of the universe. It is a revolution that is already beginning to reshape our world, to give us new tools, new technologies, and new ways of interacting with reality. It is a testament to the fact that the strangest, most counterintuitive, and most philosophically profound aspects of nature are also, very often, the most powerful and the most useful. The wave-particle duality, the central and most enduring paradox of the quantum world, is a profound statement about the nature of reality. It tells us that our classical categories of thought, our neat and tidy divisions of the world into things and processes, into matter and waves, are inadequate to describe the fundamental nature of existence. The universe, at its core, is not either-or, it is both and. An electron is not a particle that sometimes pretends to be a wave, nor is it a wave that sometimes masquerades as a particle. It is a quantum, a single, unified entity whose particle-like or wave-like aspect is revealed only in the context of a specific interaction, a specific measurement. This is Niels Bohr's principle of complementarity, a philosophical insight that is as deep as it is beautiful. The wave and the particle are two, complementary, and mutually exclusive faces of a single, underlying reality. You cannot see both faces at the same time, but you need both to have a complete picture. This is a paradox that is not meant to be solved, but to be held, to be contemplated, to be lived. And we do live it every day in the rhythm of our own consciousness. Our waking life is the particle aspect of our being. We are localized in space and time. We have a definite identity. We interact with the world as separate, discrete objects. Our thinking is linear, logical, and causal. But our sleeping life, and especially our dreams, is the wave aspect of our being. Our sense of a localized, separate self dissolves. We become a fluid, non-local field of awareness. Our thinking is associative, symbolic, and timeless. The rigid boundaries of the waking world give way to a reality that is interconnected, multiplicitous, and paradoxical. The double-slit experiment, with its strange and beautiful logic, is not just a demonstration of the duality of a single electron. It is a mirror of the duality of our own being. When we are observed by the demands of the external, social world, we collapse into a single, particle-like identity. We choose a path, we play a role. But when we are unobserved in the quiet, inner space of our own minds, in the solitude of our sleep, we are free to explore the full, wave-like potential of who we are. We can be all things at once. We can pass through all the slits of our own possibility. The wave-particle duality is not a flaw in our understanding. It is a deep, structural feature of reality itself. It is the creative tension between the one and the many, between the definite and the potential, between the collapsed world of our waking lives and the uncollapsed, superpositional sea of our dreams. To embrace this duality is to embrace the fullness of our own human experience. It is to recognize that we are both the finite, mortal beings who walk the earth, and the infinite, timeless waves of consciousness that dream the cosmos into being. The quantum vacuum, with its incessant, energetic hum of zero-point energy, is not just a strange and abstract concept of theoretical physics. It is the very womb of reality, the generative source from which all of existence arises. The idea that space, the seemingly empty void between the stars, is actually a seething, vibrant ocean of potential is a profound and revolutionary one. It tells us that the universe is not a static, finished creation, but a dynamic, ongoing process of emergence. This has a powerful and beautiful resonance with our own inner experience, the silent, empty spaces of our own consciousness, the moments of quiet contemplation, the pauses between thoughts. The deep, restorative emptiness of sleep are not voids of nothingness. They are the most fertile ground for our own creativity, our own healing, our own transformation. We live in a culture that is often deeply afraid of emptiness. We fill every moment with noise, with information, with distraction. We fear that if we stop, if we become still, we will be confronted with a terrifying void. But the wisdom of the quantum world and of the great contemplative traditions tells us that the opposite is true. It is in the silence that we can hear the subtle music of our own soul. It is in the emptiness that we can touch the source of all our creativity. Sleep is our nightly, sacred pilgrimage into this inner, creative void. As the external world of things and the internal world of ego structures dissolve, we are given the chance to connect with the pure, undifferentiated potential of our own being. This is not a passive state. It is a state of deep, unconscious processing, a state where the fragmented experiences of the day are integrated, where emotional wounds are cleansed, and where the seeds of new insights and new perspectives are sown. A dream is a virtual particle born from the vacuum of the mind. It is a fleeting, symbolic, and often mysterious expression of the deep creative processes that are at work in our inner silence. These dreams, like the virtual particles of the vacuum, can have real and powerful effects on our waking lives. They can bring us wisdom, They can bring us healing. They can bring us a new sense of purpose and direction. To learn to value silence. To befriend our own inner emptiness. To trust in the generative power of our own sleep. This is to align ourselves with the most fundamental creative principle of the universe. It is to understand that all true creation, whether of a galaxy, a work of art, or a new and more integrated self, is born not from frantic, effortful doing, but from a deep and patient surrender to the silent, secret, and life-giving power of the void. The quantum vacuum is not just out there in the vastness of space. It is in here, in the very ground of our own being. And every night, as we close our eyes and let go, we are returning home to this sacred, creative source. The quest to understand the universe and our place within it is a journey that has led us to the very frontiers of human knowledge, to the edge of space, of time, and of our own comprehension. We have grappled with the paradoxes of the quantum world, with the mysteries of dark energy and the multiverse, with the deep philosophical riddle of consciousness itself. And in this journey, we have discovered a universe that is far stranger, more beautiful, and more mysterious than our ancestors could ever have imagined. It is a universe born from a creative void, a universe of probability and potential, a universe that is not a static, clockwork machine, but a dynamic, evolving, and participatory reality. And we, as conscious, questioning, and dreaming beings, are not separate from this universe. We are an integral and essential part of its ongoing story. We are the universe's way of knowing itself, of feeling itself, of wondering at its own magnificent existence. The future of this quest is bright and full of promise. A new generation of powerful telescopes, of gravitational wave detectors, of particle accelerators will continue to push back the frontiers of our knowledge to provide us with new data, new insights, and, no doubt, new and even deeper mysteries. We are living in a golden age of discovery, a time when the answers to some of the oldest and most profound questions of humanity may be within our reach. But this quest is not just a scientific one, it is also a deeply personal and spiritual one. The insights of modern physics, with their emphasis on interconnectedness, on potentiality, on the participatory nature of reality, are not just abstract theories. They are also powerful and transformative metaphors for our own inner lives. They invite us to see ourselves not as isolated, separate egos, but as entangled, superpositional, and endlessly creative beings. They invite us to find the sacred in the silence, the potential in the emptiness, the wisdom in the uncertainty. And they invite us to honor the deep, mysterious, and restorative power of our own sleep. To see it not just as a biological necessity, but as a nightly pilgrimage to the quantum heart of our own being. A time to reconnect with the source of all creativity, all healing, and all change. The journey is far from over. The greatest discoveries, the most profound revelations, may still lie ahead, waiting patiently for us in the deep, silent, and beautiful darkness that lies just beyond the horizon of our current understanding. But the quest itself, the shared, human adventure to understand our cosmic home and our place within it, is a journey that gives our fleeting lives a meaning, a purpose, and a dignity that can rival the stars themselves. And as you close your eyes and let the universe of your own mind unfold in the quiet theater of your dreams, you can feel a sense of participation in this grand human adventure. The consciousness that is about to journey into the mysterious inner cosmos of sleep is the same consciousness that is, at this very moment, reaching out to the stars, listening for the echoes of creation, and striving to read the silent, beautiful, and endlessly fascinating story of the universe. Good night. And may your dreams be as vast and as wonderful as the cosmos itself.